In this presentation we will study the thermodynamic properties of real gases and introduce an equation of state that gives a better description of their behavior compared with the one obtained from the ideal gas law. We start with the introduction of the compressibility factor of real gases characterizing the deviation from the behavior expected for an ideal gas, particularly at high pressures. We also describe a simple approach called Burnett method to measure its value without using the critical constants of the gas. Then we present an approximation called von der Waals gas with a cubic equation of state containing parameters specific to the given substance. This equation of state describes the behavior of real gases and their thermodynamic properties better than the ideal gas law. However, the von der Waals equation of state is only an approximation and predicts non-realistic thermodynamic states in certain regions of the pressure versus volume diagram of any substance related to its phase transition. We will therefore talk about a graphical method called Maxwell construction, which is used to identify the boundary points on isotherms that correspond to saturated phases of the gas or liquid. Then we derive a general form of a universal equation of state for von der Waals gases called reduced equation of state by using the critical constants of the gas, and apply it to establish the law of corresponding states telling us that substances behave alike at the same reduced states. Reduced thermodynamic states also allow us to construct generalized charts for the compressibility factors of different substances. We also determine the internal energy of real gases by using the von der Waals equation of state and show that it depends on the properties of the given substance as opposed to its universal expression obtained for an ideal gas. Based in this finding, we will present and interpret the Joule-Thomson effect observed in the throttling of a real gas, which is the change in its temperature as it expands through a porous plug in an insulated chamber. Then we will calculate the entropy of a real gas in von der Waals approximation together with its fugacity or effective pressure with respect to the free enthalpy of the gas. Finally, we present some of the improved equations of state as the modifications of the von der Waals equation applying a more realistic description of the intermolecular forces in real gases, vapors, and liquids, which are frequently used in thermodynamic calculations. In order to describe the behavior of real gases in thermodynamics, we start with the ideal model describing the behavior of gases, that is with the ideal gas law. When we combine Boyle's law, Charles's law and Gay-Lussac's law into one formula, we obtain the ideal gas law describing the equation of state for n-mole ideal gas occupying the volume V at the pressure P and the absolute temperature T, which is the following. The pressure P times the volume V is equal to the amount N of the gas, times the universal gas constant R, times the absolute temperature T. We also showed that how the three gas laws arise as special cases of the combined gas law. In the case of isothermal processes where the gas temperature is constant, we obtain Boyle's law stating that the pressure P times the volume V is constant. We also plotted a family of isotherms for given temperatures T1, T2, T3 and so on in the pressure versus volume diagram of the gas, which are hyperbolas. The range of validity of the ideal gas law with respect to the behavior of real gases was represented by a color gradient in the diagram. Over the area of the lower pressure range, the transition from dark green to a brighter shade indicates that the ideal gas law gives more accurate approximation for dilute gases, that is for low density and low pressure. In the case of isobaric processes, the gas pressure P is constant, and we saw that the volume V of the gas is proportional to its absolute temperature T, which is Charles's law. This form of the law shows the advantage of the absolute temperature scale over the other scales of temperatures, since the actual volume of the ideal gas is directly proportional to the gas temperature measured in Kelvin. Here no reference volume is needed to formulate the law as opposed to the case where the temperature is measured in Celsius. The isobars in the volume versus temperature plot consist of a family of lines starting from the origins of the axes, which represent the absolute zero and a vanishing volume. The tangent of each isobar depends on the given values P1, P2 and so on of the gas pressure. At low temperatures the gas law is not valid, since the volume of an ideal gas shrinks to zero when we cool it down to absolute zero. The condensation of real gases shows that we cannot use the equation of state for an ideal gas at low temperatures. The law gives a good approximation only at higher temperatures indicated by the bright green area in the diagram. In the case of isochoric processes where the volume V of the gas is constant, we found that its pressure P is proportional to its absolute temperature T formulated in Gay-Lussac's law. Here we also saw that the gas pressure is directly proportional to the temperature given in Kelvin, and we do not need to apply any reference pressure measured at a given temperature as in the case of the Celsius scale. The isochores in the pressure versus temperature plot consist of a family of lines starting from the origins of the plot, which represent the absolute zero and a perfect vacuum. The tangent of each isochores depends on the given values V1, V2 and so on of the volume of the gas. According to this law, the pressure of the gas also vanishes at absolute zero, which is not the case in nature due to the condensation of gases. This law only gives a good approximation at high temperatures and low pressure, indicated by the bright green area in the middle right side of the diagram. These findings related to the range of validity of the three gas laws and its combined form in the ideal gas law follow from the study of the behavior of real gases. When we compare this behavior, that is the relation between the pressure, volume and temperature of a given amount of real gas with predictions given by the equation of state of an ideal gas, we will find the deviations from the behavior of an ideal gas presented here. Then we need to describe this deviation quantitatively, and draw some conclusion from the results that could help to construct a better model with new equations of state describing the behavior of real gases more adequately. In order to describe this deviation quantitatively, we will introduce the compressibility factor of real gases as follows. We have seen that the behavior of real gases often deviate from the behavior of an ideal gas, that is the observed or measured relationships between the state variables of a real gas, that is its volume, pressure and temperature, are not accurately described by the ideal gas law. The form of the ideal gas law can be simplified if we define the molar volume Vm of n mole gas by the ratio of its volume V to n with the unit or cubic meter per mole. Then we measure the deviation of the behavior of n mole real gas confined in the volume V at the temperature T and pressure P from the ideal gas law, given by the equation stating P times Vm is equal to the gas constant R times T, by introducing the deviation factor Z of the real gas and write its equation of state in the form stating that P times V is equal to Z times R times T. We call this deviation factor the compressibility factor of the real gas, and it is given by the ratio of the product of the pressure P of the real gas and its molar volume Vm to the product of the gas constant R and the absolute temperature T of the gas, where the pressure, the volume and the temperature are measured for a given amount of real gas. The name compressibility factor indicates that it can be defined for a given real gas as the ratio of the molar volume Vm of the real gas at a given temperature T and pressure P, to the molar volume Vm of an ideal gas at the same temperature T and pressure P, if we divide the equation of state of the real gas by the ideal gas law. We note that the reciprocal of the square root of the compressibility factor Z, known as the supercompressibility factor F for given pressure P and volume V, is also in use. Here we show the compressibility factor of a given amount of gas measured at a given temperature for hydrogen, oxygen, carbon dioxide and methane as a function of gas pressure. By definition, the compressibility factor is equal to 1 for an ideal gas, and as the diagram shows, Z tends to 1 at low pressures for all the types of gases. The very different curves for the deviation factor seen in the diagram also indicate that Z as a function of pressure, density or volume, and temperature must be measured for each type of gas, since it is not a universal function for real gases. We can also see that its value generally increases with pressure and, as we will see, decreases with temperature. Although each type of gas has its own unique compressibility factor represented by the different curves in the diagram, it is possible to give a general description for all gases based on a theorem called the principle of corresponding states. This principle will be presented when we construct a more realistic equation of state for real gases, and we will apply a universal description of the deviation factor as a consequence of the theorem. We will see that such a description provides a general method to determine this factor for each gas from measurements. We present further plots of the compressibility factor of real gases as a function of their pressure for different temperatures based on measurements. We chose 3 types of gas, such as hydrogen, nitrogen and oxygen, plotted for different temperatures between 0 degrees Celsius and 200 degrees Celsius, that is between 273.17 Kelvin and 473.17 Kelvin. The families of the plots for the deviation factor versus pressure measured at constant temperatures are very different for the 3 species, but we can still make some general statements on them. All the 3 diagrams show that the compressibility factor is approximately equal to 1 at low pressures and at high temperatures, and real gases behave as an ideal gas at atmospheric and standard conditions. We can also see in the diagrams of nitrogen and oxygen that at low pressures the volume of a real gas is generally lesser than the volume of an ideal gas at the same pressure and temperature. This property makes a real gas highly compressible at low pressure, that is, the gas can be significantly reduced in volume when subjected to relatively small pressure. This is also true for hydrogen, but this effect can only be observed at temperatures lower than about 200 Kelvin, where the compressibility factor is less than 1 at low pressures. As pressure steadily increases, the deviation factor decreases to a minimum. Again, this effect can be measured for hydrogen at low temperatures as well. The compressibility factor increases above 1 at high pressures and the real gas becomes incompressible, that is, its volume cannot be significantly reduced even if a high pressure is applied on it. We summarize the behavior of real gases over the different regimes in this table. In the first line we show the regime where the compressibility factor is less than 1. By definition, it means that the molar volume Vm of a real gas is less than the molar volume Vm of an ideal gas at the same pressure and temperature. This inequality shows that the product of the pressure P of a real gas and its molar volume Vm is less than the gas constant R times the absolute temperature T of the gas. In the second line of the table we show the case of unit compressibility factor, where the molar volumes of the real and ideal gases are equal at the same pressure and temperature. Then the ideal gas law holds, telling us that the pressure P of the real gas times its molar volume Vm is equal to the gas constant R times its absolute temperature T. Here the ideal gas law gives a good approximation of the equation of state of the real gas. In the third line we consider the case when the compressibility factor is greater than 1, that is, the molar volume Vm of a real gas is greater than the molar volume Vm of an ideal gas at the same pressure and temperature. As a result, the product of the pressure P of the real gas and its molar volume Vm is greater than the product of the gas constant R and its absolute temperature T. The second line of the table indicates that a real gas can behave as an ideal one where the ideal gas law provides a good description of the relation between its state variables in a given regime of these variables. However, the first and last line together with the plots clearly show that its behavior has a non-negligible deviation from the ideal gas law over a wide range of the state variables. Based on these findings, we conclude that the fundamental assumption made on gases at the beginning of our study on thermodynamics, stating that a gas is a continuous substance, is not tenable, and it cannot be used to completely explain the behavior of real gases. In fact, the idea that a gas is not a mere continuous medium was already shuffled into our discussion when we started to use the amount of matter measured in moles as one of the properties of gases. We established that the unit of mole appearing even in the ideal gas law describes a given amount of gas species measured in the number of particles that form the continuous substance of gases dealt with under standard condition. Then we need to assume that real gases are composed of a large number of very small particles called atoms or molecules that are in constant motion. The distance separating the gas particles is large compared to their size, and these particles in constant motion collide each other in the wall of the container of the gas. We also assume that there is an interaction between the particles colliding with each other, and between the wall and the particles bouncing off the wall. We will apply these assumptions on the discrete nature of real gases and attempt to explain the deviation of their behavior from the behavior of an ideal gas. Apart from the second line in the table describing the case of an ideal gas, we need to interpret the other two cases for real gases. If we consider the regime described in the first line of the table, we see that the volume of a given amount of real gas is smaller than the volume that would be allowed for the same amount of ideal gas at the same pressure and temperature. This indicates that there is an interaction between the gas particles that is attractive in its nature, and the moving atoms or molecules of the gas species pull on each other. This attraction helps the particles get closer together and they occupy a smaller volume than it is expected if the gas were acting as an ideal gas. In the case of the regime described in the third line of the table, the volume of a given amount of real gas is greater than the volume of the same amount of ideal gas at the same pressure and temperature. This effect is explained as follows. As pressure increased, the gas particles are crammed closer and closer together. Because they have a finite size, the atoms or molecules start pushing the other atoms or molecules away harder. As a result, they will occupy greater volume than it is expected if the gas were acting as an ideal gas. Based on the considerations of these effects, a new equation or new equations of state of real gases can be introduced, providing a more adequate description of the behavior of real gases. Before introducing the equation of state for real gases, which will help us to find an efficient method to determine their compressibility factor, we present a simple procedure called Burnett method to measure the deviation factor of real gases. In the measurement we can use an apparatus similar to the one used by Joule in his original experiment on the free expansion of air. As seen in the figure, the apparatus consists of two gas containers which are connected with a tube and placed into a vessel filled with water, serving as a calorimeter. The gas containers are denoted by the letters A and B in the figure. The tube is closed with the valve separating the two containers from each other. The container B has an outlet closed with another valve which is attached to a vacuum pump. The container A of volume VA is filled with a gas at a high pressure P0 and at an absolute temperature T, whereas the container B of volume VB is evacuated. We assume that the whole system is in thermodynamic equilibrium, and we can apply the modified gas law to describe the relationship between the state variables of the gas in the container A. Then we write that the initial pressure P0 of the gas times its volume Vi, is equal to the compressibility factor Z0 times the amount of species N0 of the gas times the gas constant R times the absolute temperature T of the gas. If we open the valve of the tube connecting the two containers while the valve of the outlet is closed, then we let the gas in the container A expand into the evacuated container B. When Joule performed his experiment, he found the free expansion of air did not change the temperature of the gas, that is, the gas had an isothermal expansion. However, in his experiment the initial pressure of the air was only about 20 bar, where the compressibility factor of real gases is still close to 1, and the ideal gas law provides a satisfying approximation of the behavior of the gas. If the initial pressure P0 is 10 times greater than the pressure applied by Joule, then the behavior of the real gas has a non-negligible deviation from the one predicted by the ideal gas law. In this case we can measure a change in the temperature of the expanding gas, which is an effect characteristic of real gases, and it will be studied after the introduction of a new equation of state for real gases. In this measurement we will wait until the thermostat can equalize the temperature of the expanded gas in the containers at the temperature T. When the thermodynamic equilibrium of the system is achieved, we measure the pressure P1 of the gas, and write its equation of state in the form stating that the pressure P1 times the sum of the volumes VA and VB, is equal to the compressibility factor Z1 times the amount of species N0 of the gas times the gas constant R times the temperature T. If we divide the second equation of state by the first one, then we can write the ratio of P1 to P0 times the ratio of the sum of VA and VB to VA as the ratio of Z1 to Z0. As a result, the compressibility factor Z1 in the first step can be expressed by the ratio of the pressure P1 in the first step to the initial pressure P0, times RV times the compressibility factor Z0, where RV is the ratio of the volume expansion of the gas, that is the ratio of the sum of VA and VB to VA. The containers are identical in the figure and they have the same volume, but in practice a Burnett apparatus applies a container B that has a much smaller volume than the container A in order to produce only small changes in the pressure of the gas after its expansion. Then RV is somewhat greater than 1. Now we close the valve connecting the containers and then we open the valve of the outlet of the container B so that we can evacuate the gas from it by using the vacuum pump. After completing the evacuation of the container B and closing the valve of its outlet, we have restored the original condition but with less amount of gas in the container A at a lower pressure at the same temperature. In the second step, we measure the pressure P1 of the gas left in the container A and where the state of the equation of the gas is the following. The pressure P1 of the gas times its volume VA, is equal to the compressibility factor Z1 times the amount of species N1 of the gas times the gas constant R times the absolute temperature T of the gas. Now we let the gas in the container A expand into the evacuated container B again by opening the valve of the tube connecting the two containers. We wait until the temperature of the expanded gas reaches the temperature T of thermostat and the system attains thermodynamic equilibrium. Then we can measure the pressure P2 of the expanded gas, and write its equation of state in the form stating that the pressure P2 times the sum of the volumes VA and VB, is equal to the compressibility factor Z2 times the amount of species N1 of the gas times the gas constant of the temperature T. If we divide this equation of state by the one obtained in the previous step, then we can express the compressibility factor Z2 in the same form as in the first step, that is by the ratio of the pressure P2 to the pressure P1, times the ratio of volume expansion RV, times the compressibility factor Z1. By substituting the expression obtained for Z1 in the first step into the right-hand side, we can write it as the ratio of P2 to P1, times RV squared times Z0. In the end of the second step we close the valve separating the containers, open the valve of the outlet of the container B, and evacuate it by using the vacuum pump. Then we can continue the same procedure with the third step. After K steps, we will able to express the compressibility factor Zk by the ratio of the pressure Pk to the initial pressure P0, times the ratio of volume expansion Rv to the power of K, times the initial compressibility factor Z0. The right-hand side is equal to Z0 over P0, times Rv to K, times Pk. If the ratio of Z0 to P0 is known and the ratio of the volume expansion Rv is given by the geometry of the apparatus, then the measurement of the pressure Pk of the gas is enough to calculate the compressibility factor Zk of the gas in the step K. In fact, it may be difficult to determine the exact ratio of volume expansion Rv due to the complex internal geometry of the system formed by containers, pipes and valves. However, we can divide the equation of state in the step K by the equation of state in the step K-1 as seen in the first step. If we assume that K is big enough that the pressures Pk-1 and Pk measured in the steps K-1 and K tend to 0, then the compressibility factors Zk-1 and Zk in the equations of state in these two steps tend to 1. As a result, the ratio of volume expansion RV can be written as the limit of the ratio of the pressure pk-1 to the pressure pk, where k formally tends to infinity or the pressure tends to 0. In practice, as k increases, the ratio pk-1 to pk converges to a finite value of RV, and we can stop the measurement process in any step where we reach the demanded accuracy of the ratio of volume expansion. One can use helium gas to evaluate this ratio from the experimental pressure ratio data, since helium with its small atomic volume and weak inter-atom interaction is close to an ideal gas with a unit compressibility factor. Other candidate for this measurement would be hydrogen, but it is far less safe to handle. We still need to know the ratio of Z0 to P0 to determine Zk. If we plot the ratio of volume expansion RV to K times the measured pressure Pk in the step K versus the pressure Pk itself, then we obtain a series of data points. With the increasing number of the steps K, the pressure Pk decreases and the compressibility factor Zk approaches 1. Then the value of RV to K times Pk given by P0 over Z0 times Zk tends to the ratio of the initial pressure P0 to Z0, that is the fitting line over the data points will intersect the y-axis at value of P0 over Z0. After having determined this value from the graph, we can insert its reciprocal into the right-hand side of the equation describing the compressibility factor Zk. Then the later will be evaluated in any step K, that is for any measured value of the pressure Pk, and we can compile the compressibility factor versus pressure chart of the gas at a given temperature T. Studying the deviation of the behavior of real gases from the ideal gas law led us to introduce the discrete nature of gas with the following assumptions. Real gases are composed of a large number of molecules, whether monoatomic or polyatomic, that are in constant random motion. For the sake of simplicity, we will call the gas particles molecules even if they are atoms, as in the case of noble gases. The distance separating the gas molecules is much greater than their size. Although they are not point-like particles and have a finite size and volume, molecules are still small enough to be able to move about fairly freely in space. There also exist repulsive and attractive intermolecular interactions in a real gas that are weak but increasing with the decreasing distance between the molecules. Since the gas particles are separated rather far from each other, they interact only very weakly. Gas molecules in random motion collide with each other and with the walls of the container, and these collisions are considered perfectly elastic. This means that a small fraction of the gas particles is always interacting strongly, that is colliding. The nature of the collisions is determined by the intermolecular interactions, that is the repulsive and attractive forces between the colliding partners. The pressure of a gas arises from molecules striking the walls of the container. The assumption on the perfectly elastic nature of the collisions between the molecules is a reasonable one, since we expect no change in the average kinetic energy of the gas molecules constantly colliding with each other and the wall. If the gas in an isolated system where no energy, momentum and mass are transported between the system and its surroundings is in thermodynamic equilibrium, then its state variables like its internal energy do not change in time and it remains in equilibrium. When we present the kinetic theory of gases and the molecular theory of heat, we will discuss in more detail how the discrete nature of gases described here allows us to interpret the macroscopic state variables of a gas such as its pressure or internal energy based on the random motion and collision of gas molecules. Now we only give some figures to show how freely gas particles can move in a given spatial volume. In the study of the ideal gas law, we introduced the standard conditions for temperature and pressure by stating that 1 mole ideal gas in such conditions, that is at 0 degrees Celsius and atmospheric pressure, occupies 22.41 liters. Then the amount of species in 1 cubic meter gas at the same pressure and temperature is given by the ratio of 1000 liters to 22.41 liters, which is equal to 44.64 moles. Since the number of particles in 1 mole of substance is given by the Avogadro's number Na, the number of particles in n moles of gas is equal to n times Na, that is 44.64 moles times 6.022 times 10 to 23. Then the number of particles in 1 cubic meter gas is about 2.69 times 10 to 25. If we want to obtain the average volume per molecule in 1 cubic meter, that is the average volume enclosing a single molecule in constant random motion within the spatial volume of 1 cubic meter, then we need to divide 1 cubic meter by the number of molecules in this spatial volume, that is by 2.69 times 10 to 25. This gives 3.72 times 10 to minus 26 cubic meter of average volume per molecule. Now we estimate the linear length associated with the size of this average volume enclosing a single particle by assuming that its cube is equal to the average volume per particle. Then this linear length describing the mean distance between the molecules can be written as 3.72 times 10 to minus 26 cubic meter to the power of 1/3, which is about 3.34 times 10 to minus 9 meters. As a result, the mean distance between the molecules of a gas in standard conditions for temperature and pressure is approximately equal to 33 angstroms. Although this value is derived for an ideal gas, the deviation factor of real gases in standard condition is close to 1, and this distance is still a good approximation in a real situation. There are several methods to determine the molecular diameter for gas species. For example, measuring gas viscosity and apply the kinetic theory of gases provide good estimations for molecular diameters. From such measurements, one can establish that the average molecular diameter for gas species, for example the species in air, is about 3 angstroms. Then we see that the intermolecular distance is about 10 times the size of the molecules in standard conditions. In the case of dilute gases, there are less molecules are enclosed in the same spatial volume, that is, the number of molecules per volume is less and the average intermolecular distance can be much greater than in a gas at atmospheric pressure. As a result, the size of the molecules becomes negligible compared with the intermolecular distance, that is, the gas particles will have more space to move without colliding with one another and the number of collisions will decrease. At the same time, the short-range intermolecular forces become weaker for the ensemble of particles with a greater average intermolecular distance, and these forces become negligible in a dilute gas. In such a situation we have the ideal gas condition, where the ideal gas represents point-like molecules moving freely without any interaction. This means even an ideal gas considered as a continuous substance has a discrete nature, and all its macroscopic properties emerge from the quantities describing the state of the randomly moving and colliding point-like particles in space, as it will be discussed in the kinetic theory of gases. We attributed the deviation of the behavior of real gases from the ideal gas law to the interactions between the gas molecules, that is, to the intermolecular forces acting on the particles of finite size moving randomly in a real gas. When the Dutch physicist Johannes Diederik van der Waals developed his theory on real gases in 1873, he postulated these intermolecular forces, now called van der Waals forces, which are weak electrostatic forces that attract neutral molecules to another in gases, liquids and solids, and are dependent on the distance between the molecules. Van der Waals forces may arise 3 distinct types of interaction: by orientation, induction or polarization, and dispersion. The interaction by orientation are often referred to as Keesom interaction after the Dutch physicist Willem Hendrik Keesom, who developed a mathematical description for dipole-dipole interactions. Although such an interaction exists between charges in ionic molecules, Keesom force normally refers to the interaction between the electrically neutral molecules of some species that are permanent electric dipoles. A molecule with permanent electric dipole moment has a distortion in the distribution of electric charge in its structure, and the molecule has a positive and negative end. Because one side of the molecule is always somewhat positive and the opposite side somewhat negative, permanent dipoles have the tendency to align with each other, and this effect results in a net attractive force between them. Keesom interaction includes quadrupole interactions in the molecules whose symmetry is lower than cubic, or in general interactions between permanent multipoles. It is important to note that Keesom interactions are temperature dependent. The second interaction of the van der Waals triad is the interaction by induction or polarization, named after Peter Joseph William Debye, the Dutch physicist and chemist who identified its existence. Debye force is caused by the interaction between permanent dipoles and other molecules, which results in the formation of induced dipoles. Permanent dipoles temporarily distort the electron clouds of other polar or non-polar molecules in their vicinity, inducing their further polarization. Then an additional attractive force arises from the interaction between a permanent dipole with a nearby induced dipole, which is independent of temperature, unlike Keesom interactions. The interaction by dispersion is the third interaction associated with the van der Waals forces, which is also called London dispersion force, since the German physicist Fritz Wolfgang London was the first to recognize this type of interaction between instantaneous or temporary dipoles and molecules. The electrons fluctuating within the electron cloud of a nonpolar molecule have the flexibility to move between electron orbits far away from the nuclei of the molecule and produce a temporary dipole moment. The average of this instantaneous polarization over a short time interval may be 0, and time-varying dipoles cannot align themselves with the actual force of attraction in their vicinity. However, they are able to interact with adjacent molecules and induce properly aligned polarization them, resulting attractive forces. These forces are believed to be the weakest of all van der Waals forces, and the strength of the London dispersion force between two molecules depends entirely on the polarizability of the molecule. Overall, the van der Waals interaction consists of two opposing forces, a long-range attraction and a short-range repulsion. The curve representing the von der Waals potential energy between two interacting molecules is given by the combination of the attractive and repulsive forces. The long-range weak attractive part of the potential is due to the permanent or induced electric dipole moments between molecules, that is, to mutual electrostatic polarization. When the distance between the molecules is greater than 0.6 nanometers, the forces are extremely weak and can be neglected. When the distance between the molecules ranges from 0.6 to 0.4 nanometers, the forces are attractive. They increase slightly as the separation distance between two molecules is reduced until they are so close together that their electron clouds begin to overlap and repel each other electrostatically. This repulsion is therefore due to the size of the molecules and opposes the attractive force as the intermolecular separation decreases. The combined force goes to zero when the interatomic distance reaches approximately 0.2 nanometers, denoted by R0, which is about the length of a typical chemical bond. At closer distances, the combined force becomes very repulsive in nature. When von der Waals developed a discrete model of real gases to describe their behavior by applying the molecular theory of matter, he introduced corrections in the ideal gas equation based on these two characteristics of the electrostatic intermolecular forces in gases. Von der Waals introduced a model for real gases based on the long-range weak attractive and the short-range strong repulsive characteristics of the intermolecular electrostatic forces. These characteristics result in two simple corrections of the picture of ideal gas, that is, the model of point molecules moving independently and colliding with the walls to exert pressure on it. The first correction recognizes the effect of short-range strong repulsive intermolecular forces. We saw that the short-range strong repulsive part of the von der Waals forces has a repulsive core whose radius R0 is of the order of 0.2 nanometers or few angstroms, depending on the chemical bond in the molecules. By separating the effects of the repulsive core and the attractive tail, the repulsive core excluding a certain space around a molecule can be interpreted as the spatial volume occupied by the molecule, so other molecules have less room in which to move. Molecules are therefore not point particles, but each has a finite volume of its own, which is described by the radius R0. In this model we can interpret the short-range strong repulsive intermolecular interaction as the result of the interaction between two sphere-shaped molecules with given size and volume described by an effective radius, although the structure of molecules is not necessarily spherical symmetric. If we apply a hard sphere model of the gas molecules with the effective radius R0 or the diameter d, then there will be a distance of closest approach between any pair of particles in the gas. Smaller intermolecular separations are forbidden, as the von der Waals potential suddenly increases to infinity. As a result, the total available volume to the system is less than the total volume of the container enclosing the gas, where the available volume can be expressed as the difference between the volume of the container and the excluded volume that is not accessible to the system. This excluded volume is represented by the spheres of the radius d enclosing the two molecules when they are at closest contact. The volume inside these spheres is not accessible for the center of the neighboring molecule. The excluded volume can be written as the number of molecules N in the system, times a parameter b' describing the excluded volume per particle. Now we determine this excluded volume for the two spheres of effective radius R0 at their minimum separation, where the distance between their centers is the diameter d of the spheres. Then the volume Vp of the particles is given by 4/3 times pi times the cube of their radius R0, which is equal to 1/6 times pi times the cube of their diameter d. Because the radii of spheres of exclusion are exactly equal to d in the hard sphere model, their volume Ve is given by 4/3 times pi times the cube of d, which is equal to 8 times the volume of the particles. This is the total excluded volume for two molecules in the hard sphere model. Hence, the excluded volume per particle is just half of this value, that is, the parameter b' is equal to 2/3 times pi times the cube of d, or 4 times the volume of the hard spheres modeling the molecules. As already mentioned, the molecules are generally not spherically symmetric and the effective radius are not describing the repulsive core of their von der Waals potential as an approximation applied for the hard sphere model. Another description of the repulsive force between nearby molecules is the soft sphere model, which allows some overlap between the molecules in a close contact, reducing the distance between the centers of the spheres, and in turn the excluded volume per particles for molecules. Because we normally use the amount of species instead of the number of molecules in the system, we introduce the parameter b defined by the product of Avogadro's number Na and the excluded volume per particle b'. Then the excluded volume in the system given by N times b' is equal to N over Na times b. The ratio is simply the amount of species n in the container, and the excluded volume in the system is equal to n times b. Now the available volume for the gas molecules in the container is given by the difference between the volume V of the container and the excluded volume N times B prime. As a result, the volume correction for a real gas in a container of volume V is given by the volume V, minus the amount of species N of the gas in the container times the parameter B. The second correction applied for real gases arises from the existence of the long-range weak attractive part of the von der Waals potential. A molecule of a gas in the interior of the container is acted upon by the von der Waals forces in all directions due to the presence of other molecules, which thereby tend to cancel. The pressure of a gas arises from molecules striking the wall of the container, but a molecule approaching the wall experiences a net backward attraction to the neighboring molecules. As a result, a molecule in a real gas hits the wall with less kinetic energy compared with the case of an ideal gas, and the attractive force in turn reduces the effective pressure that the molecule exerts on colliding with the wall. Because each gas particle is attracted to the particles in its neighborhood, we would expect the average energy of the intermolecular attraction to be proportional to the number of interacting pairs of molecules or the density of molecules in the neighbor of any given molecule. This local density can be approximated by the average density ρ bar of the gas, that is the number of molecules N per the volume V of the container. The total energy of attraction for N particles in the system is then proportional to N squared over the volume V. This mutual attraction of the molecules leads to a reduction in volume at the same pressure, acting on the molecules like an additional pressure-like term. As a result, the diminution of the pressure proportional to the number of interacting pairs of molecules at the wall is also proportional to the total energy of attraction for all the molecules per unit volume, that is to A prime times the square of the number of the molecules N per the square of the volume V. Here the constant of proportionality A prime is a parameter determined by the properties of the real gas. As in the case of the volume correction, we can introduce another parameter A given by the square of the Avogadro constant Na times the parameter A prime. Then the product of N squared and A prime is given by N squared over Na squared, times A, which is equal to the square of the amount of species N times the parameter A. As a result, the pressure correction of a real gas at the pressure P in the container of volume V is given by the pressure P, minus the square of the number of gas molecules N in the container times the parameter A prime over the square of the volume V, or the pressure P, minus the square of the amount of species N in the container times the parameter A over the square of the volume V. These two corrections for volume and pressure are introduced for the state variables of a von der Waals gas to provide a better description of the behavior of real gases. Now we apply these corrections in the ideal gas law for N-mole gas, stating that the pressure P of the gas is equal to the amount of species N times the gas constant R times the absolute temperature T of the gas, over the volume V of the gas. In this formula we replace the volume V with V minus the amount of species N times the parameter B, and the pressure P with P minus the square of the amount of species N times the parameter A, over the square of the volume V. The von der Waals constant A gives the pressure correction of a real gas per the square of the molar density of the gas, and its unit is equal to Pascal times meter raised to the power of 6, over mole squared, or bar times liter to 6 over mole squared. The von der Waals constant B gives the volume correction of a real gas per unit mole, and its unit is cubic meter per mole, or 1000 liters per mole. By applying these corrections in the equation of state of the ideal gas, we can write the pressure P as the amount of species N times the gas constant R times the temperature T over the difference between the volume V and N times B, minus N squared times A over V squared. In the corrected equation of state we express the pressure P of N mole of von der Waals gas as a function of its volume and absolute temperature, where the parameters are the gas constant R, the amount of species N, and the two von der Waals constants A and B. If we use this formula, we can also express the temperature T of the gas or its volume V as a function of the other two state variables and the parameters. The gas constant R is a universal constant, and for a given amount of gas either written in moles or in number of particles we only need to specify the von der Waals constants A and B to describe the equation of state for a von der Waals gas. Because these constants depend on the physical properties of a real gas that is on its molecular structure, we obtain different equations of state for different gas species as opposed to the ideal gas law. If we move the second term from the right-hand side of the equation to the left-hand side and multiply the result by V minus N times B, we obtain the standard form of the von der Waals equation stating that the sum of the pressure P and the square of the amount of species N times the constant A over the square of the volume V, times the difference between the volume V and N times the constant B, is equal to the gas constant R times the absolute temperature T. In a more convenient form of the von der Waals equation, we use the molar volume Vm given by the ratio of the volume V to the amount of species n, and we can state that the sum of P and A over Vm squared, times the difference between Vm and B, is equal to R times T. If we multiply the von der Waals equation by the square of the volume V, we immediately see that it is cubic in the volume of the gas, as opposed to the ideal gas law which is linear in V. Then we expect that the von der Waals equation with its two constants specific to the type of the gas describes the behavior of real gases better than the ideal gas law. However, the von der Waals gas is still an approximation of the equation of state of real gases, which can be seen as follows. The corrected form of the ideal gas law expressed in the terms of the molar volume states that the pressure P is equal to the gas constant R times the temperature T over the difference between the molar volume Vm and the constant B, minus the constant A over Vm squared. Because the first term in the right-hand side can be written as 1 over Vm, times R times T over 1 minus B divided by Vm, P times Vm over R times T is equal to 1 over 1 minus B divided by Vm, minus A over R times T times Vm. Now we do the Taylor expansion of the first term in the right-hand side at 0 by using the formula for the function 1 over 1 minus x with the series 1 plus x squared plus x cubed and so on. Here x denotes B over Vm, and P times Vm over R times T can be written as minus A over R times T times Vm, plus 1, plus B over Vm, plus the square of B over Vm, plus the cube of B over Vm and so on. If we gather the terms with the same power of Vm, then we obtain the following series. 1, plus the difference between B and A over R times T, times 1 over Vm, plus B squared over Vm squared, plus B cubed over Vm cubed and so on. In the left-hand side we recognize the compressibility factor of the gas, which is expressed by a power series with respect to the reciprocal of its molar volume Vm. We can see the zero-order expansion gives the ideal gas law where the compressibility factor is equal to 1. In the case of the von der Waals gas there are higher-order terms, but only the first-order term has a temperature-dependent coefficient. From the second-order term all the coefficients of the terms are equal to the constant B raised to some power, which indicates that this series is still some kind of approximation of the compressibility of the gas. The general case is given by the virial expansion, where the coefficients of the terms in the expansion depend on the temperature of the gas. These temperature-dependent coefficients called virial coefficients can be calculated for real gases up to an arbitrary order in statistical mechanics. As we have already seen, the equation of state of a von der Waals gas depends on the material properties of the gas, where this dependence is manifested in the von der Waals constants A and B representing the effects of the interactions between the gas molecules on the behavior of the gas. The constant A provides the correction due to the variation in the molecular structure of the particles in the gas, whereas the constant B gives the correction due to the variation in the size of the gas molecules. The table shown here contains the von der Waals constants for several species from simple molecules to more complex ones, demonstrating why these corrections arise from the properties of the molecules of a real gas. For the light elements constituting the gas molecules both the corrections are the smallest, like the atomic gas of helium which has a compact atomic structure and a small size compared to other species in the table. The von der Waals constants of the hydrogen gas are somewhat greater since the structure of a hydrogen molecule is less compact and its size is greater than that of a helium atom. These corrections are gradually increasing with the increasing complexity of the structure and the size of the molecules, as seen in the case of heavier elements like nitrogen and oxygen or the water molecule. For bromine molecules formed by atoms having more than 4 times more electrons than the oxygen atom, the constants A is almost an order of magnitude greater than the same constants for oxygen molecules. The constant B of the volume correction is also almost 2 times greater for bromine than oxygen. In the cases of alkanes like butane, octane and decane the corrections are more than 1 order of magnitude greater than those for the light element. These figures illustrate that real gases constituted of more complex molecules have a relatively high compressibility factor, and the conditions where their behavior can be approximated by the ideal gas law are very limited. In such a situation the von der Waals equation with the proper constants A and B gives much more satisfactory description of the behavior of a real gas. The von der Waals constants can be determined from the experimental data for a given gas. A straightforward method is to measure the pressure, volume and absolute temperature of a given amount of gas and compile a data series of the state variables of the gas. For example, when we determine its compressibility factor by applying the Burnett method, we obtain a chart for the compressibility factor versus pressure for a given temperature and volume. This measurement can be performed at different temperatures by changing the temperature of the thermostat in the Burnett apparatus. As a result, we obtain a data series of the relation between the pressure and the temperature of a real gas confined in a given volume. Then we can use the von der Waals equation to fit the data with respect to the parameters A and B in the equation, and the best fit provides the von der Waals constants for the given gas species. However, there is a more precise method to determine these constants based on the critical temperature, pressure and volume above which gases cannot be liquefied. When we study the isotherms of the von der Waals equation of a given real gas, we will see how its von der Waals constants can be determined from its critical constants. At the same time, the relationship between the critical constants of a real gas and the constants of the von der Waals equation also indicates that the application of the model of the von der Waals gas may turn out to be helpful in the study of phase transitions of matter. Because the aforementioned critical constants are the state variables of a gas at its critical point, we will examine this special state for von der Waals gases. In the equation of state of a von der Waals gas, the pressure P of the gas is expressed by the gas constant R times the absolute temperature T of the gas over the difference between the molar volume Vm of the gas and its volume correction constant B, minus the pressure correction constant A of the gas over the square of its molar volume Vm. Since the correction constants A and B depend on the properties of the gas, the pressure of different gases will be a different function of the molar volume at a constant temperature, as opposed to an ideal gas. That is, the isotherms of the equation of state are different for each substance. In order to illustrate the difference, we will give different examples for the pressure versus volume diagram of three types of gases by plotting their isotherms over a wide range of temperature. The first example is the hydrogen gas with the von der Waals constants A equals 0.2453 bar liter squared per mole squared, and B equals 0.02651 liter per mole. Here we plotted the isotherms of the gas in the pressure versus molar volume diagram for the range of temperature between 12 Kelvin and 92 Kelvin with the temperature intervals of 2 Kelvin. In the second example we show the isotherms of the oxygen gas with the von der Waals constants A equals 1.382 bar liter squared per mole squared, and B equals 0.03186 liter per mole. For oxygen the temperature already covers a greater range between 55 Kelvin and 365 Kelvin. And the isotherms are drawn in 10 Kelvin intervals. The isotherms in the third example are plotted for the butane gas with the von der Waals constants A equals 13.89 bar liter squared per mole squared, and B equals 0.1164 liter per mole. In the plot the range of temperature shifted to even higher temperatures in the range between 165 Kelvin and 1105 Kelvin with the temperature intervals of 20 Kelvin. Although the scales in these three pressure versus volume diagrams are different due to the different von der Waals constants, the structure of the family of isotherms is determined by the mathematical form of the equation of state, which is the same in each case. We can see a critical isotherm plotted with red color separating two sets of isotherms in each diagram. This critical isotherm at a critical temperature Tc has one point of inflection which is called the critical point of the von der Waals gas. The critical temperature is 33.3 Kelvin for hydrogen, 154.8 Kelvin for oxygen, and 425.1 Kelvin for butane. The green and yellow regions cover the two set of isotherms separated by the critical isotherm in the pressure versus volume diagrams, where we also show the critical point K of the von der Waals gas, that is the point of inflection on the critical isotherm. The first set of isotherms running in the green region belong to temperatures greater than the critical temperature Tc of the gas. The common properties of these isotherms are the following. All of them are monotonic decreasing functions of the volume of the gas, and they approximate hyperbolas with increasing temperature. This shows that at low pressure and high temperature a von der Waals gas acts as an ideal gas. It is important to mention the condition for low pressure since the vertical asymptote of the hyperbolas is not located at the volume equals 0 line. There is a minimum volume which a given amount of gas composed of molecules with finite size can be compressed in the von der Waals model, described by the volume correction constant B of the gas. The second set of isotherms running in the yellow region belong to temperatures lower than the critical temperature Tc of the gas. These isotherms have a local minimum and a local maximum which approach each other with increasing temperature, and merge in the point of inflection that is in the critical point K at the critical temperature. As a result, the isotherms monotonically increase in the region between their local minimum and maximum, depicted by the orange areas in the diagrams. In this region the pressure of the gas increases with its volume at a constant temperature, which cannot be a physical state of a real gas, indicating that it is an unstable region for the von der Waals model. This is the region of the phase transition between gas or vapor and liquid, and the critical point K determines where the medium can exist in a multi-phase state in the pressure versus volume diagram. Now we determine the state variables, that is the temperature, pressure and volume of a von der Waals gas in the critical point K of the gas. Because the critical point is a point of inflection of the pressure as a function of the volume, its first and second order derivatives with respect to the molar volume at a constant temperature vanish in the critical point. If we substitute the expression for the pressure P of the von der Waals gas into its first order derivative with respect to the molar volume Vm at a constant temperature T, we obtain minus the gas constant R times the temperature T over the square of the difference between the molar volume Vm and the volume correction constant B, plus 2 times the pressure correction constant A over the cube of Vm. This expression must be 0 in the critical point K. Similarly, the second order derivative of the pressure P with respect to the molar volume Vm at a constant temperature T is given by 2 times R times T over the cube of the difference between Vm and B, minus 6 times A over Vm raised to the power of 4. This expression also vanishes in the critical point K. We can move the second terms in the left-hand side to the right-hand side of both the equations, and divide the first equation by the second one. This gives an equation stating that the difference between Vm and B divided by 2 is equal to Vm over 3. Now we can express the molar volume Vm at the critical point from this result as 3 times the volume correction constant B of the von der Waals gas. This quantity called critical volume V sub mc can also be given by 3 times the amount of species and the gas times B, denoted by Vc and measured in cubic meter. We have expressed the critical volume of a von der Waals gas in terms of a von der Waals constant, and we can do the same with the critical temperature as well. If we evaluate the vanishing first-order derivative of the pressure with respect to the molar volume and the critical point, then we can write the equation stating that minus the gas constant R times the critical temperature Tc over the square of the difference between the critical molar volume V sub mc and the constant B, plus 2 times the constant A over the cube of V sub mc is equal to 0. Here the critical molar volume V sub mc is given by 3 times B, which we substitute for the derivative. As a result, we obtain another equation stating that R times Tc over 4b squared is equal to 2 times A over 27 times B cubed. By solving it for Tc, we can express it as 8 times A over 27 times B times R. In order to express the pressure in the critical point in terms of the constants A and B, we can use the equation of state evaluated in the critical point, which states that critical pressure Pc is equal to R times the critical temperature Tc over the difference between the critical molar volume V sub mc and the constant B, minus the constant A over V sub mc squared. Now we insert the critical molar volume and the critical temperature expressed in terms of the von der Waals constants into the equation of state evaluated in the critical point. After simplifying the two terms on the right-hand side, we obtain 4 times A over 27 times B squared, minus A over 9 times B squared, which gives A over 27 times B squared. We conclude that the critical constants of a von der Waals gas are the following. The critical temperature Tc of the gas is equal to 8 times the pressure correction constant A over 27 times the volume correction constant B times the universal gas constant R. The critical pressure Pc of the gas is given by the pressure correction constant A over 27 times the square of the volume correction constant B. The critical molar volume V sub mc of the gas is equal to 3 times the volume correction constant B, or alternatively the critical volume Vc is given by 3 times the amount of species N of the gas times the constant B. We note again that the critical constants of a von der Waals gas are its state variables in its critical point, which is a unique physical state represented by the point of inflection on the critical isotherm of the gas. We already mentioned in the discussion on the von der Waals constants that the critical pressure of a substance is required to liquefy a gas at its critical temperature. This means that the critical point designate the top of the unstable region in the pressure versus volume diagram, where the critical phenomenon of phase transition of a gas can take place and where liquid and gas coexist. We also mentioned in the previous section that the von der Waals constants of a gas can be determined from its critical constants. We immediately see that the volume correction constant B can be expressed by 1 over 3 times the critical molar volume V sub mc, whereas the pressure correction constant A is equal to 27 times B squared times the critical pressure Pc. The later can also be written as 3 times the square of 3 times B, times Pc, that is 3 times V sub mc squared times Pc. Instead of pressure, we can write the constant A in terms of temperature by using the formula obtained for the critical temperature. Then we have 27 times B over 8, times R times Tc, or 9 over 8 times V sub mc times R times Tc. These expressions show that we can determine the von der Waals constants of a real gas, which are essentially parameters emerging from a theory of approximating the behavior of the gas, if we are able to measure the critical constants of the real gas. Now we look at how to determine the critical point of any substance, that is to measure its critical constants. Such a measurement is performed by using a so-called critical point apparatus shown in the photos with two different implementations. It is a high-precision device for studying the compression and liquefaction of a gas and recording its isotherms in the pressure versus volume diagram. The apparatus includes a transparent measuring cell which is highly resistant to leakage and compression, enclosed in a transparent water chamber serving as a part of a thermostat. The volume inside the cell can be changed via a finely adjustable handwheel for both the types of devices. The apparatus in the first photo uses a capillary as the measuring cell made from an extremely strength glass, and a glass cylinder as a water chamber. The lower meniscus of a mercury column in the capillary shows the position that can be read for the determination of the volume. The mercury is supplied from a stainless steel pressure chamber sealed to the measuring capillary. For the apparatus seen in the second photo, the change in the volume of the measuring cell is indicated by a combination of a fixed and a rotary scale to a high accuracy. The device uses hydraulic oil instead of mercury, where the measuring cell and the hydraulic system is separated by a membrane that moves as the volume of the cell increases. A thermostat circulating the water in the water chamber allows the temperature to be maintained at a highly constant value in the measuring cell of both the types of apparatus, which can be monitored by means of a thermometer. After setting the temperature of the thermostat and allowing temperature equalization between the water bath and the gas to take place, the temperature of the system can be read from the scale of the thermometer. In the first apparatus, the pressure chamber must be filled with the sample gas and its pressure is measured by a manometer. In the second apparatus, the pressure is the output of the hydraulic system, since the pressure gradient between the measuring cell and the chamber of oil is negligible. The determination of the critical point and the state variables of the sample in the critical point is the following. In the case of the first apparatus, the pressure chamber can be filled with the sample by connecting it with the container of the sample gas and opening its inlet valve. In order to clean any residues of gas from the pressure chamber, it must be evacuated for at least 30 minutes, which removes the gas dissolved in the mercury. By turning the hand wheel, the gas will be compressed until the mercury column is visible in the measuring capillary. With suitable gases, an increasing liquefaction of the gas can be seen above the mercury meniscus on increasing compression. In the case of the second apparatus, we have a similar procedure. After the gas container of the sample is attached to the device, the measurement cell must be flushed several times with the sample gas to eliminate air from the system. At the beginning of the measurement, the inlet valve is closed and the volume of the measuring cell is set to a given value. At the initial volume, the inlet valve is open to fill the cell and reach an initial pressure. Then the valve can be closed and the hand wheel can be turned to decrease the volume of the cell while monitoring the increasing pressure. The volume of the compressed gas in the cell is read from the combined fixed and rotary scale when the gas starts to liquefy in the transparent measuring cell. The measurement with these devices is based on visual information, since it is possible to observe the formation of the first drops of liquid and disappearance of the last gas bubbles during transitions from the gaseous to the liquid phases and vice versa. During the phase transition, the critical volume can be determined from the height of the mercury column or the position of the combined scale on the measuring cell. The corresponding pressure values are indicated by the manometer measuring the pressure of the cell. The critical temperature can also be determined by controlling the thermostat to find the minimum temperature above which no phase transition is detected for arbitrary compression of the gas. In such a way, the state variables of a given amount of gas, that is its critical temperature, pressure and volume, can be measured by the apparatus when the phase transition of gas is observed in its critical point. Before presenting some data as a result of the measurement of the critical constants of various substances, we introduce the critical compressibility factor of the gaseous phase of a medium, which is simply its compressibility factor determined in its critical point. That is, the critical compressibility factor ZC of a gas is defined by the product of the critical pressure Pc and the critical volume V sub mc over the product of the gas constant R and the critical temperature Tc, where all the critical constants are measured for the given gas. If we apply this definition for a von der Waals gas, we can substitute the critical constants expressed in terms of the von der Waals constants. Then Zc is given by 1 over the gas constant R, times the pressure correction constant A over 27 times the square of the volume correction constant B, times 3 times B, times 27 times or times B over 8 times A. This gives 3 over 8, that is, the critical compressibility factor Zc in the von der Waals approximation is equal to 0.375. Showing the critical compressibility factor is universal for all von der Waals gases. This table contains the critical constants of the substances already used to illustrate the variation in the von der Waals constants between different types of gases. The figures in the table show that the critical constants tend to increase with the size of the molecules. It is helium with its monoatomic molecule that has a compact structure with the lowest critical constants in the table. Its critical temperature is about 5 Kelvin, its critical pressure is less than 1 megapascal, and its critical molar volume is only somewhat greater than 0.05 cubic meter per kilomole. All the critical constants are greater for the gas composed by hydrogen molecules. Its critical temperature and critical pressure are already one order of magnitude greater than those of the helium, and its critical molar volume is also greater than 0.06 cubic meter per kilomole. By considering molecules of elements that have greater atomic numbers in the periodic table like oxygen, nitrogen, and bromine, we see that the critical temperatures are one order of magnitude greater than those of the light elements. Their critical pressures are also several times larger than the critical pressure for the hydrogen molecule. There is some increase in their critical volume as well, but it is much more moderate. Indeed, their volume correction constants are not much greater than those for the molecules of light elements. Not surprisingly, the water molecule has even higher critical temperature and critical pressure, although its critical molar volume remains very small. In the case of substances composed of organic molecules like alkanes, we find that butane, octane and decane have somewhat lower critical temperatures than water, and their critical pressures remain in the range of the critical pressures of oxygen and nitrogen. Nevertheless, their critical molar volumes are at least one order of magnitude greater than those of the other substances shown in the table, indicating that their volume correction constants are also the greatest among them. We also display the critical compressibility factors EC for each substance in the last column of the table. By comparing the values in this column with the value computed from the von der Waals equation, we can see that the values measured for the real gases are always less than the one derived for von der Waals gases. This deviation simply indicates the fact that the von der Waals gas is only an approximation describing the behavior of real gases. Because the deviations are smaller for gases composed by lighter molecules than for heavier elements or more complex molecules, we conclude that the approximation is more accurate for molecules with more compact structures. We have already seen that the equation of state for a von der Waals gas is a cubic equation in the volume of the gas, which expresses the pressure P of the gas as the gas constant R times the temperature T of the gas over the difference between the molar volume Vm of the gas and the volume correction constant B, minus the pressure correction constant A over Vm squared. If we multiply this equation by the difference between Vm and B, and factor out the parentheses, then we obtain the cubic equation stating that Vm cubed, minus the sum of B and R times T over P times Vm squared, plus A over P times Vm, minus A times B over P is equal to 0. In this equation the von der Waals constants are fixed for a given gas, and the temperature determines which isotherm is considered in the pressure versus volume diagram. As we have already discussed and as the isotherms for hydrogen show, the solutions of this algebraic equation can be separated into two, or including the critical isotherm, three classes. If we consider temperatures greater than the critical temperature Tc of the gas, then the equation have one real root. For the critical isotherm where the temperature is equal to Tc, the cubic equation has triple roots, that is three roots that are equal, whereas in the case of temperatures less than the critical temperature we will find three different roots. Because the critical point of a von der Waals gas is a point of inflection of its critical isotherm, the cubic equation has triple roots in the critical point. The value of the triple roots is the critical molar volume V sub mc of the von der Waals gas. As a result, we can write that the cube of the difference between the molar volume Vm of the gas and its critical molar volume V sub mc, that is Vm cubed, minus 3 times V sub mc times Vm squared, plus 3 times V sub mc squared times Vm, minus V sub mc cubed is equal to 0. By comparing this equation with the one above evaluated in the critical point, we can identify the multiplication factors in the two equations as follows. 3 times V sub mc must be equal to B plus or times Tc over Pc, 3 times V sub mc squared must be given by A over Pc, and V sub mc cubed must be equal to A times B over Pc. We can express the pressure correction constant A from the second relation as 3 times V sub mc squared times Pc, which we already derived from the conditions of the vanishing first and second order derivatives of the von der Waals equation in the critical point. If we substitute this result into the third relation, we can write the cube of V sub mc as 3 times V sub mc squared times Pc times B, over Pc, that is 3 times V sub mc squared times B. Then we express the critical volume V sub mc as 3 times the volume correction constant B again. By inserting this formula into the first relation and solving it for Tc, we obtain the ratio of 8 times A over 27 times or times B, as expected. Here we have just re-established that the relations between the critical and von der Waals constants of a gas allow one to determine the von der Waals constants of a gas by measuring its critical constants. Now we examine the class of the solutions to the cubic equation for which the temperature is less than the critical temperature. Since the equation has three different roots in the region indicated by the yellow and the orange areas, each isotherm has a point of inflection between a local minimum and a local maximum. This fact has already been established from the isotherms of hydrogen, oxygen and butane, and we also saw that minima and maxima of the isotherms enclose an unstable region indicated by the orange area in the diagram. In the unstable region the pressure increases with volume, that is the gas has a negative compressibility. This means that any isotherm passing through this region cannot be an equilibrium state for the gas or the substance. As the measurements performed by any critical point apparatus demonstrate, a gas-liquid phase coexist in the unstable region. A continuous phase transition can be observed between gases or vapors and fluids while the pressure stays constant. When the phase transition is complete, the pressure starts to change at a given volume. It will increase after a complete liquefaction and decrease after a complete vaporization of the medium. In order to provide a correct description of the behavior of von der Waals gases in a thermodynamic state within the unstable region of the pressure versus volume diagram, James Clerk Maxwell, the famous Scottish physicist and mathematician, introduced a graphical method called Maxwell construction to identify the boundary points on isotherms that correspond to saturated phases of the gas or liquid. Maxwell started with the observation about the general assumption on the homogeneity of medium in a vessel. If a phase transformation of the medium must be taken account, then we cannot expect that its spatial distribution remains homogeneous, and it may be in completely different thermodynamic states during liquefaction or vaporization. If we consider an isotherm of a von der Waals gas at the temperature less than the critical temperature in the pressure versus volume diagram, and pinpoint different thermodynamic states on it from the state A to the state G with the states C and E at the local maximum and the local minimum of the isotherm, then we can see that the pressure of the medium in the states B and F is the same, but its volume and density are very different. Here the states B, D, and F are chosen such that the system has the same pressure. Maxwell assumed that the medium may evolve directly from the state B to the state F along a horizontal isobaric path instead of passing through the intermediate states C, D, and E. In this way a gas or vapor is liquefied along the isobaric path between the rarefied state B and the fully condensed state F, and the isotherm of the medium is represented by the broken curve A, B, D, F, and G. When Maxwell constructed this broken curve isotherm replacing the original one derived from the solution of the von der Waals equation, he used the following arguments. If one is able to prevent the saturated vapor from condensation, the medium can also brought from the state B to the state C along the green curve. Similarly, by carefully keeping the liquefied medium from contact with vapor and preserving it in the liquid condition, the medium may also be brought from the state F to the state E along the green curve. However, the red curve C, D, and E represents unstable states where the isothermal compressibility of the substance is negative. These states cannot therefore be realized, and as Maxwell put it, this curve must be handled only as a hypothetical path in the pressure versus volume diagram representing the physical states of the medium. Then he considered a closed hypothetical path where the medium passes from the state B to the state F along the curve B, C, D, E, and F while staying homogeneous, and returns to the state B along the horizontal isobaric line between F and B as a liquid-vapor mixture. Because the curve B, C, D, E, and F is a part of an isotherm and the temperature does not change along the horizontal path between the states F and B during vaporization, the temperature is constant in the whole process. As a result, no heat can be converted into pressure-volume work during the thermodynamic cycle. The pressure-volume work done in the process is given by the total area of the closed curves F, D, E, and B, C, D in the pressure versus volume diagram, where the sign of the area is determined by the direction of the path along which the system evolves. The total area representing the work is then the area of the closed curve F, D, E, minus the area of the closed curve B, C, D, which must vanish as no net work is done in the isothermal process. This tells us that the areas of the closed curves F, D, E, and B, C, D must be the same, and the Maxwell construction applies it as a criterion to determine the boundaries of the phase transitions represented by the states B and F on the isotherms of a von der Waals gas. By identifying these points, a part of the isotherm between the points B and F, including the unstable branch between the points C and D, can be replaced by the isobaric horizontal line connecting the points B and F. As already mentioned, This means that any isotherm of von der Waals gases below the critical temperature is replaced by the isotherm represented by the broken curve passing through the points A, B, D, F and G determined for each isotherm. If we use the graphical method determining the equal areas of the closed curves for the unstable branches of these isotherms, then each of them can be replaced by an improved isotherm where a horizontal line represents the unstable region of phase transition in the pressure versus volume diagram. We note that the region of instability covers a smaller area in the diagram than the region where the phase transition takes place, and their boundaries only meet in the critical point K. When we describe the different branches of an improved isotherm based on the phases of matter evolving along the isotherm, we can state the following. The isotherm between the states A and B describe the thermodynamic state of medium, when it is an overheated vapor. If the medium is in the state B, then we talk about a dry, saturated vapor of low density which is about to condense or liquefy. The isotherm between the states B and F is the stage of the vapor-liquid phase transition of the medium along the horizontal branch at constant pressure. In the state F the medium is already completely liquefied and it is called saturated liquid of high density. If we reverse the direction of the evolution of the medium along the isotherm, then F denotes the state where the saturated liquid is at boiling point and is about to vaporize. After presenting Maxwell's arguments for the graphical method, we discuss how to apply them for a real thermodynamic system, for example a gas in the measuring cell of a critical point apparatus. Here the system is the medium in the measuring cell, and its surroundings consist of the water chamber containing the cell with the thermostat serving as a heat bath, and the mechanics changing the volume of the cell. Let us consider the reversible isothermal thermodynamics cycle for the medium along the closed path B, C, D, E, F, D and be used in the Maxwell construction. This cycle is hypothetical in the sense that it passes through the unstable states along the curve C, D, E, and it is a quasi-static reversible process where there is no entropy production. We can apply the first law of thermodynamics for the medium in the measuring cell stating that the infinitesimal amount of heat Q absorbed from or released to the heat bath by the system is equal to the infinitesimal change in its internal energy U, plus the pressure P of the medium times the infinitesimal increase or decrease in the volume V of the cell. We integrate this equation over the closed path, where we determine the contribution of each term to the change in the state variables of the system in the thermodynamic cycle. Because the system has returned into its initial state, the total change in its internal energy U is equal to 0, that is the cyclic integral of the internal energy vanishes. Then the total heat exchanged between the medium in the cell and the water chamber is equal to the cyclic integral of its pressure P with respect to its volume V. At the same time no entropy is generated in the system during the reversible cycle, and the differential of the entropy S of the system integrated along the closed path vanishes. By applying the definition of entropy, we can write the left-hand side as the cyclic integral of 1 over the absolute temperature T of the medium with respect to the heat Q exchanged between the system and its surroundings. Since the cycle is isothermal, the right-hand side is equal to 1 over the temperature T times the total heat exchanged between the medium and the heat bath during the cycle. If we substitute the result obtained from the first law into this equation, we will have 1 over T of the cyclic integral of P with respect to V which must be equal to 0. The cyclic integral of the pressure with respect to the volume describes the pressure volume work done on the medium in the measuring cell by the mechanical part of the apparatus compressing the medium, or on a mechanics by the expanding medium. We note that the mechanics only allows the gas to expand if the volume of the cell is changed by the hand wheel of the apparatus. Then the result tells us that the pressure volume work done by or on the system vanishes, where we can break up the path into two branches along which the integration is performed. The first integral is computed along the closed curve B, C, D, B, and the second one along the closed curve D, E, F, D. The sum of these integrals must be equal to 0. By changing the direction of the integration in the second term, we can write that the integral of the pressure with respect to the volume along the closed curve B, C, D, B is equal to the integral of the pressure with respect to the volume along the closed curve D, F, E, D. Because these integrals in the pressure versus volume diagram of the medium are given by the areas of the closed paths along which the integrals are computed, we conclude that the areas enclosed by these two curves must be equal. Here the states C and E are determined by the isotherm for a given temperature, and the task is to find the states B and F which also determine the state D by evaluating the equal areas of the two closed paths of the thermodynamic cycle. The most straightforward method to find the equal areas is the usage of a fine grid on the pressure-volume diagram, where the cells covered by the areas of the two closed curves can be counted. By using a trial and error method, the difference between the counts determined for both the areas must vanish for the proper choice of the boundary points. Evidently this method has a limited accuracy, and nowadays various numerical methods are applied for the Maxwell construction. They are normally include some combination of numerical integration schemes and root-finding algorithms with iterative techniques. There are several different ways to do Maxwell construction, and we show here a simple method to determine the boundary volumes of the phase transition of the medium based on the equal areas for an isotherm at a given temperature. We saw that the pressure P of a von der Waals gas is given by the gas constant R times its temperature T over the difference between its molar volume Vm and its volume correction constant B, minus its pressure correction constant A over Vm squared. The vanishing partial derivative of the pressure P with respect to the molar volume Vm at a constant temperature T can be used to determine the local maximum and the local minimum of any isotherm at temperatures lower than the critical temperature of the gas. This condition gives the equation stating that minus R times T over the square of the difference between Vm and B, plus 2 times A over Vm cubed is equal to 0, and two of its roots are the molar volumes V sub mc and V sub me of the gas at the local extrema of the isotherm. We will use these molar volumes as a starting point to find the boundaries of the phase transition. In order to compute the area in the pressure volume diagram equivalent to the pressure volume work for an isothermal process, we will evaluate the integral of the pressure with respect to the molar volume between the minimum and maximum molar volumes occupied by the gas during its evolution. For example, the area under the isotherm between the molar volumes V sub mf and V sub md is given by the integral of the pressure P with respect to the molar volume Vm with the lower and upper limits V sub mf and V sub md. If we insert the pressure of the von der Waals gas into this expression, and perform the integration, then we need to evaluate the primitive function given by the natural logarithm of R times T over the difference between Vm and B, plus A over Vm. This gives the natural logarithm of the ratio of V sub mf minus B to V sub md minus B, plus A over V sub md, minus A over V sub mf. The rule of the equal areas tells us that the areas of the closed curves DEFD, and BC-DB must be equal in the Maxwell construction. The area of the first closed curve can be obtained by subtracting the area under the isotherm from the rectangle with the base given by V sub md minus V sub mf and with the height given by the pressure P' of the medium in the states B, D and F. Then this area is equal to P' times the difference between V sub md minus V sub mf, minus the natural logarithm of the ratio of V sub mf minus B to V sub md minus B, minus A over V sub md, plus A over V sub mf. This expression must also be equal to the area of the second closed curve, which is given by the difference between the area under the isotherm and the area of the rectangle with the base Vm sub B minus Vm sub D and the height P'. That is, the right-hand side of the equation can be written as the natural logarithm of the ratio of V sub md minus B to V sub mb minus B, plus A over V sub mb, minus A over V sub md, minus P' times the difference between V sub mb and V sub md. After simplifying this equation, we obtain the condition telling us that the pressure P' times the difference between V sub mb and V sub mf, minus the natural logarithm of the ratio of V sub mf minus B to V sub mb minus B, minus A over V sub mb, plus A over V sub mf must vanish. We use this condition to find the molar volumes V sub mb and V sub mf, where the pressure P' is determined by the evaluation of the von der Waals equation at any of these molar volumes. As an initial guess in the method finding the molar volumes, we can choose the average Vm bar of the molar volumes at the local maximum and minimum of the isotherm, which can be substituted into the von der Waals equation providing the initial pressure P bar of the numerical procedure. If we insert the pressure P bar into the von der Waals equation and solve it for the molar volume, then we obtain the other two roots V sub mb bar and V sub mf bar besides the root Vm bar, which can be used as the initial boundaries of the phase transition in the procedure. We also have the condition stating that the pressure P of the medium at the actual values of the molar volumes V sub mb and V sub mf must be equal, and apply it as the first equation to solve. Again, the pressure in these states is denoted by P'. The second equation of the system is the equation of equal areas, and the system of these two equations can be solved by applying some iterative method for finding the roots V sub mb and V sub mf, that is the molar volumes for the boundary points of the isotherm that correspond to the saturated phases of the medium. An alternative method for determining the boundary volumes of the phase transition of a medium is based on the Gibbs criterion using the Gibbs potential or the chemical potential in the Maxwell construction. When we studied thermodynamic potentials, we established that an infinitesimal change in the free enthalpy or the Gibbs potential G of a thermodynamic system is equal to minus the entropy S of the system times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. In the case of isothermal processes, this equation reduces to the relation stating that the differential of the free enthalpy is given by the volume times the differential of the pressure. Let us integrate this relation over an isothermal path from an initial state A to an arbitrary state. Then we can express the Gibbs potential G of the system as a function of the constant temperature T and the instantaneous pressure P, and write it as the initial Gibbs potential of the system in the state A, plus the integral of the volume V of the system with respect to the pressure from the pressure PA in the state A to the pressure P. Since we integrate the volume of the system with respect to the pressure, we show the molar volume versus pressure diagram for one isotherm of a von der Waals gas at the temperature less than its critical temperature, where the states B and F are the boundary states of its phase transition, and the states C and E are the states where the isotherm has the local maximum and the local minimum in the pressure versus volume diagram. Then the change of the free enthalpy G of the system evolving, for example, between the two states A and B, can simply be written as the integral of the volume V of the system with respect to the pressure P from the pressure PA of the system in the state A to the pressure PB of the system in the state B. We obtain a similar relation by applying the Gibbs-Duhem equation for a one-component system, which states that the number of molecules N in the system times the differential of the chemical potential mu of the system, is equal to minus the entropy S of the system times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. Here the number of molecules N is given by the amount of species N times the Avogadro's number Na, whereas the chemical potential mu can be expressed as the partial derivative of the Gibbs potential G with respect to the number of molecules N at constant temperature and pressure. Again, for an isothermal process, the Gibbs-Duhem equation reduces to the relation stating that N times the differential of mu is equal to V times the differential of P. This shows that the change in the Gibbs potential is given by the number of the molecules in the system times the change in its chemical potential, and the usage of the free enthalpy and the chemical potential is equivalent in this problem. As a result, the differential of the chemical potential mu is given by 1 over the Avogadro's number Na, times the molar volume Vm of the system times the differential of the pressure P. This equation can be integrated along an isothermal path from the initial state A to an arbitrary state as in the case of the Gibbs potential, which gives an equation stating that the chemical potential mu as a function at the constant temperature T and the instantaneous pressure P of the system, is equal to the initial chemical potential of the system in the state A, plus 1 over the Avogadro's number times the integral of the molar volume Vm of the system with respect to the pressure from the pressure PA to the pressure P. Then the change in the chemical potential mu of the system evolving between the two states A and B can simply be written as 1 over the Avogadro's number, times the integral of the molar volume Vm of the system with respect to the pressure P from the pressure PA to the pressure PB. Now we use the equations describing the change in the free enthalpy or the chemical potential of a medium to introduce the Gibbs condition, selecting the boundary states B and F corresponding the saturated phases of the medium. This condition states that the Gibbs potential G of any substance must be the same in the boundary states B and F of its phase transition. Or equivalently, the chemical potential mu of the medium in the state B must be equal to the chemical potential in the state F. If we compute the change in the free enthalpy and the chemical potential between the states B and F by applying the two integrals obtained here and insert these conditions into the result, then we can state that the integral of the molar volume Vm of the medium with respect to the pressure P from the pressure Pb to the pressure Pf must vanish during the phase transition of the substance between the states B and F. For the change in the Gibbs potential, we just substituted the volume V by the amount of species N times the molar volume Vm in the integral. The figure shows that the system evolving along the von der Waals isotherm between the boundary states of the phase transition must pass through the states C, D, and E. As a result, we can break up the vanishing integral from the state B to the state F to the integrals between the state B and the state C, between the state C and the state D, between the state D and the state E, and between the state E and the state F. By reversing the direction of the integration between the states C and D, and between the states D and E, we obtain the equation stating that the integral of the molar volume Vm with respect to the pressure P from the pressure Pb to the pressure Pc, minus the integral of the molar volume Vm with respect to the pressure P from the pressure Pd to the pressure Pc, is equal to the integral of the molar volume Vm with respect to the pressure P from the pressure Pe to the pressure Pd, minus the integral of the molar volume Vm with respect to the pressure P from the pressure Pe to the pressure Pf. Here we see that the first integral in the left-hand side of the equation gives the area under the isotherm between the states B and C, and the second integral gives the area under the isotherm between the states C and D. Their difference is equal to the area of the closed curve B, C, D, and B. Similarly, the first integral in the right-hand side of the equation gives the area under the isotherm between the states E and D, and the second integral gives the area under the isotherm between the states E and F. Their difference is equal to the area of the closed curve D, E, F, and D. Now we can conclude that the Gibbs condition selects the boundary states B and F for the phase transition of the medium such that the areas of these closed curves in the volume versus pressure diagram must be equal. We therefore obtain the same criterion of the equal areas derived for the pressure versus volume diagram of the von der Waals isotherms by Maxwell, that is, the application of the Gibbs criterion is equivalent to the Maxwell construction. However, the volume or the molar volume Vm of the medium as a function of the pressure P and the temperature T is a cubic equation which is an implicit function of the pressure at a constant temperature. This expression is more difficult to integrate than the pressure expressed in an explicit form as a function of volume. Fortunately, the change in the Gibbs potential can be monitored during the phase transition, which helps us to find the boundary points corresponding the saturated states of the medium on the von der Waals isotherms. In order to examine the region of the phase transition in the volume versus pressure diagram for von der Waals gases, we will derive the explicit form of their Gibbs potential. We have already seen that the differential of the free enthalpy G of a gas in an isothermal process is given by the volume V of the gas times the differential of its pressure P. We can formally divide this expression by the differential of the volume V, and write the partial derivative of the free enthalpy G with respect to the volume V at a constant temperature T, as the volume V times the partial derivative of the pressure P with respect to the volume V at a constant temperature T. If we express the left-hand side of this equation in terms of the molar volume Vm of the gas, and integrate it with respect to Vm from the molar volume in an initial state A to the molar volume in an arbitrary state, we obtain the Gibbs potential as a function of the pressure P at a constant temperature T. The right-hand side of the equation can also be written in terms of the molar volume Vm. If we insert the von der Waals equation into this form and calculate its derivative with respect to the molar volume at a constant temperature, then we obtain Vm times the sum of minus the gas constant R times the temperature T over the square of the difference between Vm and the volume correction constant B, and 2 times the pressure correction constant A over the cube of Vm. By removing the brackets we obtain minus R times T over the difference between Vm and B, minus R times T times B over the square of the difference between Vm and B, plus 2 times A over Vm squared. If we integrate this equation with respect to the molar volume between V sub Ma and Vm, then we obtain the primitive function minus R times T times the natural logarithm of the difference between Vm and B, plus R times T times B over the difference between Vm and B, minus 2 times A over Vm, which has to be evaluated at the upper and lower limits of the integral. As a result, the change in the Gibbs potential G of a system evolving from the state A is given by minus the amount of species N of the medium in the system, times the gas constant R times the temperature T, times the natural logarithm of the difference between the molar volume Vm and the constant B, plus N times R times T times B over the difference between Vm and B, minus 2 times N times A over Vm. This form can be used to determine the free enthalpy of a von der Waals gas along its isotherms passing through the unstable region. Equivalently, one can use the chemical potential μ for the same purpose since the Gibbs potential in the case is just the product of the number of molecules and the chemical potential. In the molar volume versus pressure diagram we have chosen an isotherm for which both the two states with the pressure Pe on the isotherm can be seen in the diagram. The labeling of the states along the isotherm remains the same, that is the states B and F denote the boundary states of the phase transition, and the states C and E denote the local maximum and the local minimum of the isotherm in the pressure versus volume diagram. We introduce the point H on the upper branch the isotherm, where the pressure of the gas is equal to the pressure in the state E at the local minimum. Similarly, the point J on the lower branch of isotherm represents the state where the pressure is equal to the pressure in the state C at the local maximum. Let us suppose that the system proceeds along the isotherm from the initial state A in the direction of the state H. For pressures less than pH which is equal to Pe, the molar volume of the system is single-valued and unique for given pressure and temperature. This is also the case for pressures greater than Pj which is equal to Pc, that is a system evolving along the isotherm from the state G in the direction of the state J has a single-valued and unique volume. These branches of single state on the given isotherm lie within the green regions in the diagram. However, as the pressure increases above pH or decreases below Pj, that is P is in the interval between pH and Pj or equivalently between Pe and Pc, 3 states of equal pressure become available on the isotherm. The branch representing such states of the given isotherm lies within the orange region, where any horizontal line of constant pressure will intersect the isotherm in 3 points representing the 3 available states for given pressure and temperature. For example, the states B, D, and F are such available states at the pressure PB, where 2 of these states, namely the states B and F, are stable, and the state D is unstable. This situation can be studied in more detail if we substitute the molar volume for a given pressure and temperature into the formula obtained for the Gibbs potential, or equivalently the chemical potential, and plot the result against the pressure as the medium evolves along the isotherm from the state A to the state G. First, we do not assume that the states B and F are the boundary states of the phase transition, but some arbitrary states at some pressure PB in the orange region of the molar volume versus pressure diagram. The graph of the free enthalpy versus pressure has 3 segments, where the first segment passes through the states A, H, and B, and stops at the state C. The second segment originates from the state C, passes through the state D, and terminates at the state E. The third segment starts at the state E and passes through the states F, J and G. As the molar volume versus pressure diagram shows, the first and the third segments are concave segments, where the partial derivative of the volume with respect to the pressure at a constant temperature is less than 0. This means that the system evolving along these segments is mechanically stable. The second segment of the graph between the states C and E is a convex segment, where the partial derivative of the volume with respect to the pressure at a constant temperature is greater than 0, and this segment therefore represents mechanically unstable states. Mechanical stability for a gas or a medium just means that its volume will shrink with increasing pressure. It will also maintain its physical properties without phase transition, provided the substance has also thermodynamic stability. The green and orange colors in the second diagram representing the regions with 1 unique solution or 3 available states for the molar volume show that mechanical stability does not necessarily imply thermodynamic stability. Although the mechanically unstable segment between the states C and E completely lies within the orange region where one of the available states is unstable, the other 2 mechanical stable segments pass through both the green and the orange regions. They have parts where the system has thermodynamic stability, such as the part of the first segment for pressures less than pH in the green region, and the part of the third segment for pressures greater than pJ in the other green region. In the orange region, both the first and the third segments are thermodynamically unstable. Any state on the convex segment, for example the state D, is unstable, but the Gibbs potential has local minima for the corresponding states B and F at the same pressure on the concave segments. Whether the system actually selects the state B or the state F depends on which of these local minima of the Gibbs potential is lower. As seen in the plot, the medium has lower free enthalpy in the state B, thus the state B is realized as a true physical state for the given pressure and temperature. As already mentioned, we have not assumed that the states B and F are the boundary point of the fully saturated states of the medium. By imposing the Gibbs criterion on the states B and F, we demand that the system has the same free enthalpy or chemical potential in these states, and they are located at the intersection of the 2 concave segments. As a result, both the states B and F are selected by the criterion, that is, both of them are realized in the system as the boundary states of the phase transition of the medium. The evolution of the medium along the isotherm from the state A to the state B in the molar volume pressure diagram corresponds its evolution along the first concave segment between the states A and B in the Gibbs potential versus pressure diagram. Then the physical isotherm is constructed as an isobaric line between the states B and F while passing through the state D in the molar volume pressure diagram, which corresponds the evolution along an isobaric path between the point B on the first concave segment to the point D on the convex segment, then from the point D to the point F on the second concave segment. The evolution of the medium along the von der Waals isotherm from the state F in the direction of the state G corresponds its evolution along the second concave segment from the state F in the direction of the state G. If we want to determine the boundary states B and F of the phase transition of the medium based on the Gibbs criterion, we need to solve a system of equations as in the case of the Maxwell construction. The first equation is still the one establishing the equality of the pressure in the states B and F, and the second one is the equation imposing the equality of the Gibbs potential in those states. We need to evaluate the equation describing the change in the free enthalpy evolving from the initial state B to the state F where the left-hand side vanishes. By applying some numerical algorithm to solve this system, we can obtain the pressure and the molar volumes in the states B and F of the boundary of the phase transition. We have presented a method called Maxwell construction providing the correct description of the physical state of real gases in the unstable region of the isotherms of the von der Waals gas used as an approximation. For a given von der Waals isotherm for temperatures less than the critical temperature of the gas, we had to determine the boundary points on the isotherm that correspond to the saturated phase of the medium. We have discussed two approaches to construct a physical isotherm based on findings the boundary states of the phase transition. Both of the approaches use two criteria imposed on the boundary states formulated in mathematical equations, which can be solved by applying some numerical method. The first approach of the construction of a physical isotherm suggested by Maxwell starts with the assumption of the equality of the pressure in the boundary states, that is, the pressure of the medium must be the same in both the states. The other assumption is the equality of the areas of the two closed curves formed by the intersecting von der Waals isotherm and the isobaric physical path along which the medium evolves. The second approach applies the Gibbs criterion, and also starts with the assumption of the equality of the pressure of the medium. Instead of the rule of equal areas, the criterion demands the equality of the Gibbs potential of the medium in the boundary states. Whether we follow the first or the second approach, the solution of the mathematical equations of the assumptions used in the construction will provide the volume of gas in the boundary points of the isotherm representing the saturated phase of the medium at a given temperature, and the pressure of the medium in the process of its phase transition. As a result of the Maxwell construction, the von der Waals isotherms are replaced by broken curve isotherms with isobaric paths along which the phase transition of the medium takes place, and we obtain a family of isotherms for temperatures less than the critical temperature of the medium in its pressure versus molar volume diagram. The boundary points of the phase transition define a curve known as Maxwell curve. We already mentioned that the curve of the boundary points encloses the boundary curve of the mechanically unstable region of the isotherms, and the two curves only meet in the critical point K of the medium. The critical isotherm and the Maxwell curve represent the boundaries between the different phases of the medium, that is, the different states of matter in the pressure versus volume diagram. The critical isotherm separates the green region representing the state of permanent gas from all the other states. The critical point K divides the critical isotherm and the Maxwell curve into two parts or branches. The blue area representing the liquid state of the medium is bounded by the left-hand branches of the critical isotherm and the Maxwell curve, whereas their right-hand branches form a boundary for the left-hand side of the orange region of unsaturated vapor. The yellow area under the Maxwell curve is the domain of the phase transition of the medium, where it exists in the mixed phase of liquid and saturated vapor. We note that this diagram only gives a partial information in the phase transition of real gases or substances. Here we show the so-called phase diagram, which is a pressure-volume-temperature diagram of any medium under the study of its phase transitions. We can recognize the isotherms of the medium as the intersections of the T equals constant planes with the surface displayed in the diagram, which are represented by the dashed lines. Only the critical isotherm passing through the critical point K is plotted with continuous line, which separates the domain of the state of gas represented by the green surface from the other domains of the phase diagram. We can also identify the blue, the yellow and the orange areas bounded by the critical isotherm representing the liquid vapor, and the vapor state of the medium respectively. However, the phase diagram also shows other three phases, such as the regions of the solid liquid and liquid phase transitions represented by the red and the turquoise surfaces, and the region of the solid state represented by the purple area. This diagram will be discussed in more detail when we study the phase transitions of matter. When we introduced the model of the von der Waals gas to provide a better approximation of the behavior of real gases, we found that the equation of state of the model gas described by the von der Waals equation depends on parameters specific to real gases. However, we will show that the equation of state derived for von der Waals gases can still be cast in a universal form called reduced equation of state, which is the same for any substance in the von der Waals approximation. We already derived the relations between the critical constants and the von der Waals constants, and we saw that the critical temperature Tc of a von der Waals gas is equal to 8 times its pressure correction constant A over 27 times the gas constant R times its volume correction constant B. The critical pressure Pc of the gas is given by the constant A over 27 times the square of the constant B, and its critical molar volume V sub mc is equal to 3 times the constant B. We determine the critical compressibility factor Zc of a von der Waals gas defined by the critical pressure Pc times the critical molar volume V sub mc over the product of the gas constant R and the critical temperature Tc, and found that it is equal to 3 over 8. We also express the von der Waals constants in terms of the critical constants, and we could write the pressure correction factor A as 3 times the square of the critical molar volume Vcm, times the critical pressure Pc. Similarly, the volume correction parameter was expressed by 1 over 3 times the critical molar volume V sub mc. The relationships between these two types of constants indicate that the critical constants completely determine the properties of a real gas in the von der Waals approximation, and they can be used to specify the behavior of the given real gas instead of the von der Waals constants. We therefore introduce a set of dimensionless variables describing the state of a von der Waals gas by normalizing its temperature, pressure and molar volume with their corresponding critical values. These dimensionless variables called the reduced state variables of a von der Waals gas are the following. The reduced temperature T are defined by the ratio of the absolute temperature T of the gas to its critical temperature Tc, is equal to 27 times or times B over 8 times A, times T. The reduced pressure P are defined by the ratio of the pressure P of the gas to its critical pressure Pc, is given by 27 times B squared over 8, times P. The third critical variable is the reduced volume V are defined by the ratio of the molar volume Vm of the gas to its critical molar volume V sub mc, and it is equal to Vm over 3 times B. By definition, the reduced variables measure the departure of the condition of the substance from its own critical condition. The later corresponds to the unit value of the reduced variables, and the deviation of these variables from one indicates that the substance is either in subcritical or supercritical state. Now we express the equation of state of a von der Waals gas in terms of the reduced state variables of the gas. The von der Waals equation states that the sum of the pressure P of the gas and its pressure correction constant A over the square of the molar volume Vm of the gas, times the difference between the molar volume Vm and the volume correction constant B of the gas, is equal to the gas constant R times the absolute temperature T of the gas. If we insert the formula for the constants A expressed in terms of the critical constants into this equation, then we can write the second term in the first parentheses as 3 times Pc times the square of V sub mc over the square of Vm. Similarly, the constant B in the second parentheses can be written as V sub mc over 3. After dividing this equation by the product of Pc and V sub mc, we obtain another equation stating that the sum of P over Pc and 3 times the square of V sub mc over the square of Vm, times the difference between Vm over V sub Cm and 1 over 3, is equal to R times T over the product of Pc and V sub mc. In the left-hand side we can apply the definitions of the reduced variables, and we can write it as the sum of the reduced pressure PR and 3 over the square of the reduced volume VR, times the reduced volume VR minus 1 over 3. In the right-hand side we express the ratio of R to the product of Pc and V sub mc in the fraction from the equation obtained for the critical compressibility factor Zc, and write the fraction as 8 over 3, times the ratio of the temperature T to the critical temperature Tc. By applying the definition of the reduced temperature in the right-hand side, we arrive the reduced equation of state of the von der Waals gas stating that the sum of the reduced pressure PR and 3 over the square of the reduced volume VR of the gas, times 3 times the reduced volume VR minus 1, is equal to 8 times the reduced temperature TR of the gas. Or in another form, the reduced pressure PR is equal to 8 times the reduced temperature TR over 3 times the reduced volume VR minus 1, minus 3 over the square of the reduced volume VR. As a result, we obtained an equation of state for any von der Waals gas which does not contain the volume and pressure correction factors specific to the given substance. That is, the reduced equation of state is free from the von der Waals constants and is universal for all substances. The fact that the reduced equation of state is universal since it contains no constants specific to the particular substance allows us to establish a correspondence between the thermodynamic states of different media for which the reduced equation of state is equally valid. If we enclose some amount of different substances in two vessels labeled by the numbers 1 and 2, we can bring them into given thermodynamic states described by the temperature T, the pressure P and the volume V. The state variables of the corresponding substance are also labeled by 1 and 2. Because the substances are different, their critical constants are also different. For both the media we can define the reduced variables by the ratio of their state variables to their corresponding critical constants. In the general case, the state variables are not the same in the two systems, however it is possible to prepare the states of the substances such that their reduced variables are the same. If this condition holds, then we say that the two substances are in corresponding states. For example, first we can bring both of the systems into their own critical points described by their critical constants, and then change their thermodynamic states by holding one of their reduced variables equal to 1 and modifying the other two such that the substances could have the same deviation from their critical conditions. This can be achieved in a critical point apparatus where one of the state variables of the medium in the measuring cell can be kept constant while the other two can be modified, for example by applying an isothermal expansion or compression of the substance in its critical condition. In general, when two systems, either gases or fluids, are in corresponding states, they have the same set of the three reduced variables. Although their actual state variables may differ as seen in the example, the two substances are said to be in corresponding states if their reduced temperature, pressure, and volume are the same. In fact, The existence of a universal equation of state implies that if two reduced variables are the same for a set of the systems, then the third reduced variable is also the same throughout the set of systems. That is, they are in corresponding states with a pair of equal reduced variables from the complete triplet of variables. This condition can be formulated in one principle called the law of corresponding states in the following way. There exists a universal equation of state containing no arbitrary constants if expressed in the reduced variables describing the thermodynamic state of the substance. Hence, the law of corresponding state tells us if the two of the reduced variables, for example the reduced temperature and the reduced pressure, are given for a certain medium, we can solve the reduced equation of state for the third one, here for the reduced volume of the medium, which will be the same for any other substance at the same conditions given by the reduced pressure and the reduced temperature. In other words, substances at the same reduced pressures and temperatures have the same reduced volume. This is how von der Waals discovered the principle of corresponding states and stated that substances behave alike at the same reduced states. Because substances at same reduced states are at corresponding states, the law tells us that substances at corresponding states behave alike. As a result, in the von der Waals approximation, the thermodynamic behavior of all substances is essentially the same, except for a scaling factor that is related to the critical point of the substance. Critical constants become the scaling factor by which substances can be compared among each other in terms of their departure from criticality or their reduced states. If two substances are at the same reduced state, that is, they have the same relative departure from criticality, then the law of corresponding states demands that they behave alike regardless of their nature. In this case, we say that the two reduced states correspond to one another, and we expect that the substances at these states exhibit the same behavior. Here we present the isotherms of the reduced equation of state telling us that the reduced pressure PR is equal to 8 times the reduced temperature TR over 3 times the reduced volume VR minus 1, minus 3 over VR squared. The isotherms are shown for the reduced temperature in the range between 0 and 4 with the intervals of 0.1. The critical isotherm is represented by the red curve with the critical point K of the substance at the point of inflection of the isotherm, where the reduced temperature, the reduced pressure, and the reduced volume are equal to 1. As the equation of state shows, the reduced pressure is divergent at the reduced volume equals 1 over 3, that is at the excluded volume of the molecules comprising the substance in the hard sphere model. At absolute zero, where the reduced temperature vanishes, the reduced pressure of the substance is negative as it becomes inversely proportional to minus the square of its molar volume. Therefore, the isotherm at absolute zero is completely in the region of the mechanical instability, where the von der Waals equation of state cannot describe the behavior of the substance. This can be seen if we display the regions separated by the critical isotherm and the boundary curve of the mechanical unstable region. The green area represents the states of permanent gas, the yellow area covers the region where phase transitions can take place, and the orange area represents the mechanical unstable states where the von der Waals approximation breaks down. The correct description of the medium in this region can be obtained by applying Maxwell construction for the reduced equation of state. Even with this limitation, the pressure versus volume diagram plotted for the reduced equation of state is supposed to be universal for all substance, establishing the law of corresponding states. At the same time, the law of corresponding states is not always accurate due to the fact that the von der Waals equation is only an approximation, and the reduced equation of state does not always describe the exact corresponding states of real substances. In order to illustrate the law and its approximate nature, let us consider an example for the corresponding states of different substances. In the pressure versus volume diagram, we select the thermodynamic states A, B, and C in the vicinity of the critical point K, and the table shows the reduced variables in these three states. The point representing the state A is located on the critical isotherm, that is, the critical temperature TR is equal to 1 in this state. The volume of the medium is chosen to be twice its critical volume, that is, its reduced volume VR is equal to 2. Then the reduced equation of state gives 0.85 for the reduced pressure PR. In the case of the state B, we hold the pressure of the substance at its critical value, that is, the reduced pressure stays unity, while we decrease the reduced volume from 1 to 0.6. This can be achieved by lowering the reduced temperature to 0.93 and evaluating the reduced equation of state at these subcritical values of volume and temperature. In the state C, the molar volume of the medium is held on its critical value, that is, the reduced volume is equal to 1, while the reduced temperature is raised to 1.1. For the slightly supercritical reduced temperature and the critical reduced volume, the equation of state gives 1.04 for the reduced pressure. Now we consider these three states in the case of two different substances, such as hydrogen and butane, for which we already presented the pressure versus molar volume diagrams in the discussion on the critical point of a von der Waals gas. By substituting the von der Waals constants of hydrogen into the equation of state, in this diagram we plotted a family of isotherms at given temperatures between 12 Kelvin and 92 Kelvin with the intervals of 2 Kelvin, where the critical isotherm is drawn in red color. We also saw that the critical temperature of the gas is equal to 33.3 Kelvin, whereas the pressure is given by 1.3 megapascal and the molar volume is equal to 0.0649 cubic meter per kilomole at its critical point K. For butane, the isotherms are derived from the von der Waals equation with the correction constants of butane and plotted between 165 Kelvin and 1105 Kelvin with the intervals of 20 Kelvin. The critical constants of butane were also presented before. Its critical temperature is equal to 425.2 Kelvin, its critical pressure is given by 3.8 megapascal, and its critical molar volume is equal to 0.255 cubic meter per kilomole. As in the pressure versus volume plot of the reduced equation of state, the green, the yellow, and the orange areas represent the regions of permanent gas, the mixed phases, and the unstable states in both diagrams. Now we introduce the states represented by the points A, B, and C on the pressure versus volume diagram of the reduced equation of state for both the substances. However, we need to modify some of the reduced variables shown in the table since there is some deviation between them and the solutions of the von der Waals equation containing parameters that are specific to the two substances. As mentioned before, this deviation is the consequence of the fact that the von der Waals approximation used to derive the reduced equation of state as a universal equation is not an exact description of the behavior of real gases. These two tables presenting the state variables of hydrogen and butane in the states A, B, and C illustrate the law of corresponding states and its approximate nature for the two species. The point A is located on the critical isotherms of the two substances, and in the thermodynamic state represented by this point both hydrogen and butane are at their critical temperatures, that is at 33.3 Kelvin and 425.2 Kelvin respectively. In this state both of the substances are confined in molar volumes that are twice their critical molar volumes, that is the molar volume is equal to 0.1298 cubic meter per kilomole for hydrogen and 0.51 cubic meter per kilomole for butane. The substitution of these values into the von der Waals equation containing constants specific for the two media, gives 1.22 megapascal for the pressure of hydrogen and 3.64 megapascal for the pressure of butane. By scaling the result with the critical pressures of the two substances, we obtain values of the reduced pressure that deviate from 0.85, the value specified in the table of the reduced variables. The superscript of 0.85 tell us that the reduced pressure of hydrogen is greater than 0.85 by 0.092 in the state A. Similarly, the subscript of 0.85 represents an increase of 0.101 in the reduced pressure for butane. As a result, if the two substances are in the state A, their reduced temperatures and their reduced volumes are the same, but there is a slight difference between their reduced pressures. Then hydrogen and butane in the state A have approximately the same reduced variables, or the two different substances are approximately at corresponding states. We have a similar situation in the case of states B and C. In the state B the pressures of hydrogen and butane are kept at the critical values, while the substances are compressed into the molar volume 0.6 times smaller than the critical values. That is, they are confined in the molar volumes of 0.0389 cubic meter per kilomole and 0.153 cubic meter per kilomole, and the pressure of hydrogen is equal to 1.3 megapascal and the pressure of butane is given by 3.8 megapascal. The reduced temperature of the systems is specified to be 0.93 in the state B, from which we can compute the temperatures of the two substances in this state. If these temperatures and the molar volumes are substituted into the von der Waals equations of these substances, then they are supposed to give the critical pressure for both the systems. However, there is a deviation between the results and the critical values of the pressure, and we need to modify the reduced temperatures of the system so that we could keep the reduced pressure of the two media at unity. The decrease of 0.149 in the value of the reduced temperature equivalent to 26.1 Kelvin gives 1.3 megapascal, that is the critical pressure of hydrogen, when it is substituted together with the molar volume 0.0389 cubic meter per kilomole into the equation of state. Similarly, the reduced temperature decreased by 0.279 is equivalent to 277.9 Kelvin, and we obtain the critical pressure when we substituted this value and 0.153 cubic meter per kilomole into the von der Waals equation. As a result, the states B for hydrogen and butane are corresponding states, although only approximately, due to the small difference between the reduced temperatures of the two media. In the case of the state C, we hold the molar volume of the systems at their critical values, that is the molar volumes of hydrogen and butane are equal to 0.0649 cubic meter per kilomole and 0.255 cubic meter per kilomole respectively. The reduced temperature is set to 1.01 for the two substances, which represents 33.6 Kelvin for hydrogen and 429.5 Kelvin for butane. If these molar volumes and temperatures are substituted into the von der Waals equations for the two media, then we obtain 1.46 MPa for the pressure of hydrogen and 4.4 MPa for the pressure of butane. By scaling these results with the critical pressures of the substances, we can also derive reduced pressures for them, which have some deviation from the value 1.04 specified for the state C. The reduced pressure of hydrogen is less than 1.04 by 0.083, whereas the difference is 0.119 for butane. Thus the reduced variables of hydrogen and butane are the same with a small difference in the reduced pressures in the state C, that is the states of the two media with these reduced variables can be considered as corresponding states, at least approximately. We derive the reduced equation of state by substituting the von der Waals constants into the von der Waals equation of a given substance with its critical constants and express the result in terms of the reduced variables. Now we repeat the same procedure, but we do not replace all the state variables in the equation by their corresponding reduced variables. The von der Waals equation for a given medium states that the sum of the pressure P of the medium and its pressure correction constant A over the square of its molar volume Vm, times the difference between the molar volume Vm and the volume correction constant B of the medium, is equal to the gas constant R times the absolute temperature T of the medium. Here the correction constants of the substance can be expressed in terms of its critical constants as follows. The pressure correction constant A is given by 3 times the square of the critical molar volume V sub mc of the substance, times the critical pressure Pc of the substance, whereas the volume correction constant B is equal to the critical molar volume over 3. By substituting these expressions into the von der Waals equation, we can replace the von der Waals constants with the critical constants. If we factor out the product of P times Vm from the parentheses and divide the result by the product of R times T, then we obtain an equation stating that the ratio of P times Vm to R times T, times 1 plus 3 times Pc over P, times V sub mc squared over Vm squared, times 1 minus V sub mc over 3 times Vm is equal to 1. Because the ratio of the state variables to their critical values gives the reduced variable of the state variables, we can write the terms inside the parentheses as 1 plus 3 over the product of the reduced pressure PR and the square of the reduced volume VR, and 1 minus the 1 over 3 times the reduced volume VR. Since the first factor in the product in the left-hand side of the equation is the compressibility factor Z of the medium given by the product of the pressure P and the molar volume Vm over the product of the gas constant R and the temperature T, we divide the whole equation by the second and the third factors in the product and keep the compressibility factor Z in the left-hand side of the equation. As a result, we have a function in the right-hand side of the equation which depends only on the reduced pressure and the reduced volume of the medium. The result shows that the general form of the universal equation of state for the law of corresponding states is a function of the 3 reduced state variables of any substance. The ideal gas and the von der Waals gas are special cases providing explicit forms of this universal equation. The compressibility factor Z of any ideal gas is equal to 1, stating that it does not depend on the reduced variables of the gas in this idealized model. In fact, we cannot talk about reduced state variables of an ideal gas at all, since this model does not describe any critical phenomenon in the behavior of a real gas. The von der Waals equation of state already gives a more realistic description for the universal function, and as we have seen, the compressibility factor is a function of 2 reduced state variables of the von der Waals gas. Either it can be expressed in terms of the reduced pressure and the reduced volume, or equivalently in terms of other 2 pairs of the 3 state variables. However, the von der Waals equation of state is still an approximation applied to describe the behavior of real gases, and the general form of the universal function for the law of corresponding states can only be derived from the virial expansion of realistic equations of state constructed in statistical mechanics. In such an expansion, the compressibility factor Z of a real gas is expressed as an infinite series of negative powers of the molar volume Vm of the gas, where the coefficients C2, C3 and so on are known as the virial coefficients of the expansion. These coefficients are normally written in the form of coefficients dependent on the reduced temperature over the critical molar volume V sub mc. These temperature-dependent coefficients are computed up to an arbitrary order by applying the principles and methods of statistical mechanics. We can see that the first term in the right-hand side of the virial expansion is equal to 1, that is the 0th order term of the series describes the ideal gas law. When we derived the von der Waals equation, we presented the virial coefficient in the second term in an explicit form depending on the temperature and the von der Waals constants. The first order term of the virial expansion therefore describes the von der Waals approximation. In the case of real gases, we also need to determine higher virial coefficients to provide a better description of their behavior. When we introduced the compressibility factor of real gases, we mentioned that the principle of corresponding states providing the general description of the behavior of real gases in terms of their reduced state variables, allows us to determine their compressibility factor efficiently with relative high accuracy. We saw that the graphs of the compressibility factor versus the pressure at given temperatures for various species such as hydrogen, nitrogen, and oxygen are very different. However, if the compressibility factor of different substances is plotted against their reduced pressure at a given reduced temperature, then the data points are scattered around the same curve in the Z versus PR diagram, as seen in the figure. The measured values of the compressibility factor versus the reduced pressure are plotted for 8 different substances from methane to water at reduced temperatures between 1 and 2 with the intervals of 0.1. The curves at given reduced temperatures shown here are results of the curve fitting with the measured compressibility factor of hydrocarbons. Because of this general feature, generalized compressibility factor charts can be used for many different substances in accurate thermodynamic calculations, which express the compressibility factor as a function of pressure and temperature. The most commonly used chart has been the Obert-Nelson chart, which is compiled from hundreds of data points of 25 or more different pure gases, achieving an accuracy within 1 or 2% for the compressibility factor greater than 0.6, and within 4 or 6% for Z values between 0.3 and 0.6. The parameters used in the Obert-Nelson chart are the standard reduced variables, that is the reduced pressure P are given by the ratio of the pressure P of the gas to its critical pressure Pc, the reduced temperature Tr of the gas given by the ratio of its absolute temperature T to its critical temperature Tc. The third state variable of the gas is its pseudo-reduced volume V are defined by the specific volume V of the gas over the ratio of the specific gas constant Rs of the gas times the critical temperature Tc to the critical pressure Pc. As shown here, the Obert-Nelson compressibility chart is normally presented in the form of several plots covering different ranges of the reduced pressure. The first plot contains the Z versus PR charts represented by the red curves for the reduced pressure from 0 to 1, and also includes a chart for the compressibility factor at very low reduced pressures between 0 and 0.1. The curves are plotted at the reduced temperatures between 0.6 and 5.0. The chart also has a family of blue curves representing the compressibility factor as a function of the reduced pressure at constant pseudo-reduced volumes in the range between 0.7 and 8.0 in the full chart and between 9 and 30 in the small one. The second plot of the generalized compressibility chart shows the compressibility factor as a function of the reduced pressure between 0 and 7, covering the domain of the critical point for the reduced variables. The range of the reduced temperature for the red curves is defined from 1.0 to 5.0. Whereas the blue curves are plotted at the pseudo-reduced volumes between 0.2 and 3.0. The third plot of the generalized compressibility chart covers the widest range of the reduced pressure between 0 and 40. The chart shows the red curves plotted at constant reduced temperatures between 1.0 and 15, whereas the blue curves represent the compressibility factor at the pseudo-reduced volume in the range between 0.105 and 0.6. If we want to determine the compressibility factor of a given substance of known critical constants at a given temperature and pressure by using the compressibility chart, we need to complete the following steps. First, we compute the reduced variables of the substance from its given state variables and critical constants by applying the definitions shown here for the parameters of the plots. Then we find the reduced pressure on the x-axis of the chart. From there, we move up on the chart along a vertical line until the red curve at the given reduced temperature is found. From the intersection of the vertical line and the curve, we move right along a horizontal line until we reach the y-axis. The intersection of the horizontal line and the y-axis gives the value of the compressibility factor at the given temperature and pressure of the substance. As an example illustrating this procedure, we chosen carbon dioxide from the list of substances for which the compressibility data is plotted against the reduced pressure. If we consider a vessel filled with 100-liter carbon dioxide at the pressure of 6 megapascal and at the temperature of 30 degrees Celsius, that is 303 Kelvin, then we find that the reduced pressure of the gas is 0.81 and its reduced temperature is close to unity, since the critical pressure of the gas is 7.39 MPa whereas its critical temperature is given by 304.2 Kelvin. Then we draw a vertical line from the point on the x-axis at 0.81 up to the curve plotted to the reduced temperature equals 1, and a horizontal line from their intersection to the y-axis. The horizontal line intersects the y-axis at the point 0.62, that is the compressibility factor Z of the 100-liter carbon dioxide at 6 MPa and 30 degrees Celsius is given by 0.62. Instead of the reduced temperature, we can also use the pseudo-reduced volume of the substance to determine Z in the same way by using the blue curves. When we look at the compressibility charts, we confirm the following information. At very low pressure, that is where the reduced pressure is much smaller than 1, real gases have a compressibility factor close to 1, indicating that they behave like as an ideal gas regardless of their temperature. With increasing temperature, that is where the reduced temperature is greater than 2, the compressibility factor of real gases has a moderate deviation from 1, and their ideal gas behavior can still be assumed with good accuracy. In the vicinity of the critical point where the reduced variables are equal to 1, the compressibility factor of real gases has the greatest deviation from 1 at reduced pressures less than about 10, that is, they have the greatest deviation from the ideal gas behavior. Besides this deviation in the critical region, the accuracy of the chart is limited close to the critical point due to the sensitivity of the compressibility factor to the reduced pressure and temperature. The values predicted by compressibility charts have also very large deviations from the measured values for highly polar gases due to the strong intermolecular forces between the polarized molecules. In the case of hydrogen, helium and neon, the reduced pressure and temperature must be modified at critical temperatures above 5 by scaling the state variables with the critical constants plus 8, so that one could use the general compressibility charts for such gases. Now we determine the internal energy of a von der Waals gas in a given thermodynamic state, which is equal to the internal energy of real gases under the conditions where the von der Waals approximation describes the real gas behavior accurately. When we calculated the specific internal energy U of an ideal gas of mass m at the temperature T, that is the ratio of its internal energy U to its mass m, then we found that it is equal to the specific heat capacity CV of the gas at constant volume, times the absolute temperature T. This formula shows that the only state variable which the internal energy of an ideal gas depends on is its temperature. We also established that the internal energy U of a given amount of substance is a function of its entropy S and temperature T for a fixed number of the particles N of the substance. The partial derivative of the internal energy with respect to the volume at a constant temperature for such a functional dependence contains the partial derivatives of U with respect to S and T. We could replace the partial derivatives of U with respect to S and T by applying some of the Maxwell relations and express the partial derivative of the internal energy U with respect to the volume V at a constant temperature T as minus the pressure P of the substance, plus its temperature T times the partial derivative of the pressure P with respect to the temperature T at a constant volume V. The right-hand side of this equation can be written as T squared times the partial derivative of P over T with respect to T at a constant V. If the substance is a von der Waals gas, then its pressure is given by the gas constant R times the temperature T over the difference between the molar volume Vm of the gas and its volume correction constant V, minus its pressure correction constant A over Vm squared. We can substitute this expression into the partial derivative, which gives A over the product of Vm squared and T squared. We express this ratio in terms of the volume V by writing it as the square of the amount of species N times A over the product of V squared and T squared. Here the amount of species N is equal to the mass m of the substance over its molar mass m sub m. If we substitute this result into the partial derivative of the internal energy U with respect to the volume V at a constant temperature T, then we obtain N squared times A over V squared. The number of particles N, which is fixed, can be written as the product of the amount of species N and the Avogadro's number Na, that is the number of particles N of a gas is given by the ratio of the Avogadro's number Na to the molar mass m sub m of the gas, times its mass m. Now the internal energy U of a von der Waals gas can be written as the integral of the partial derivative of the internal energy with respect to the volume at a constant temperature, where we integrate along any isothermal path between an arbitrary initial state A with the volume VA and the actual state with the volume V. The internal energy depending on the temperature T, the volume V, and the number of particles N of the gas is the sum of two terms. The initial internal energy UA of the gas in the state A, and the integral of the partial derivative of U with respect to V at constant T, where the integral is performed with respect to V from VA to the actual value of V. Because the initial state A is an arbitrary thermodynamic state, we can choose the volume VA of the system such that it tends to infinity. As a result, the average distance between a finite number of particles or molecules of the substance becomes so great that the intermolecular forces can be neglected between the molecules and the gas behaves like an ideal gas. This means that the internal energy of the system in the initial state A tends to the internal energy of the same amount of ideal gas at the same temperature. Then the internal energy of a von der Waals gas is equal to the internal energy of the same amount of ideal gas at the same temperature, plus the integral of n squared times A over V squared with respect to V from infinity to V. By substituting the expression obtained for the internal energy of the ideal gas into the first term in the right-hand side, we can write it as the mass m of the gas times its specific heat capacity CV at constant volume times its temperature T. The integral in the second term gives minus n squared times A over V. If we insert the specific volume V defined by the ratio of the volume capital V to the mass m into the second term and pull out the mass m from both of the terms, then we can write the right-hand side of the equation as m times the difference between CV times T and n squared times A over m squared times the specific volume V. Because the amount of species n is given by the ratio of the mass m to the molar mass m sub m, the second term in the parentheses is equal to 1 over the square of m sub m, times A over V. We can absorb the factor 1 over m sub m squared into the pressure correction constant A by defining the constant A prime, and write the specific internal energy U of a von der Waals gas as the specific heat capacity CV of the gas at constant volume times its absolute temperature T, minus the constant A prime over the specific volume V of the gas. This expression shows that the internal energy of a von der Waals gas or a real gas depends both on the temperature and the volume of the gas. We also note that if the volume of the von der Waals gas tends to infinity, then the second term vanishes and the internal energy of the gas reduces to the internal energy of an ideal gas which does not depend on volume. As we can see, the internal energy of a von der Waals gas is given by the sum of the internal energy of an ideal gas depending on the temperature of the gas, and a second term depending on the volume of the gas. Because the second term contains the pressure correction constant of the real gas, it is not difficult to show that this term is related to the pressure correction term in the von der Waals approximation given by the amount of species n of the gas times its pressure correction constant A over the square of its volume V. We can see the role of this term in the internal energy of the gas, if we substitute the product of the mass m of the gas and its specific volume V into the volume capital V of the gas. Then the pressure correction can be written as 1 over the square of the molar mass m sub m of the gas, times the constant A over the square of the specific volume V, or A prime over V squared. The specific pressure volume work done against the intermolecular attractive forces by the gas expanding from its minimum volume, that is its volume correction constant B, to its specific volume V, is given by the integral of the pressure correction with respect to the specific volume V from B to V. By substituting the expression obtained for the pressure correction into the integral and performing the integration, we can write the specific work as minus the modified pressure correction constant A prime over the specific volume V, plus the constant A prime over the volume correction constant B. The first term in the right-hand side is negative, indicating that the pressure volume work done by the expanding gas reduces its internal energy. The second term is a constant determined by the properties of the gas, and it can be dropped from the right-hand side when the specific pressure volume work is subtracted from the specific internal energy of the gas. In this interpretation, the internal energy of a von der Waals gas is the sum of the temperature-dependent internal energy derived from the ideal gas approximation describing the behavior of the real gas in zeroth order, and the correction term minus A prime over the specific volume V describing the work done against the intermolecular forces between the gas particles in the von der Waals approximation. The fact that the internal energy of a real gas depends on its volume has the obvious consequence that the gas must cool down during its expansion. We already discussed the free expansion of an ideal gas when we presented the experiments on the expansion of air that was performed by Gay-Lussac in 1807 and Joule in 1845. The apparatus used by Joule in his experiment consists of two identical gas containers connected with a tube that has a valve, and placed into a vessel filled with water serving as a calorimeter. The valve is closed, separating the containers of volume V1, and one of them is filled with air at a given pressure P1 and temperature T1. In the experiment, the valve is opened, and the gas is free to expand so as to fill the entire volume V2 of the containers. After the final equilibrium state has been reached, the temperature T2 and the pressure P2 of the whole system are measured. The total volume V2 of the system is given by 2 times the volume V1 of the individual containers. The first law of thermodynamics tells us that the change in the internal energy of the gas due to its expansion is equal to the sum of the heat Q absorbed by the gas and the pressure volume work W done on the gas. Since no heat flowing through the walls of the containers is measured by the calorimeter, and no pressure volume work is done on the rigid walls of the containers, the difference between the internal energies U2 and U1 vanishes. That is, the specific internal energy of the gas is the same before and after its expansion. The specific internal energy of a real gas is given by the difference between its specific heat capacity CV at constant volume times its temperature T, and its modified pressure correction constant A' over its specific volume V, and this expression can be substituted into the first law. This gives an equation stating that CV times T1 minus A' over V1, minus CV times T2 plus A' over V2 vanishes. If we express the difference between the temperatures T2 and T1, we can write it as A' over CV, times the difference between 1 over V2 and 1 over V1. Here the relationship between the volumes capital V1 and capital V2 of the gas before and after its expansion shows that its specific volume V2 is greater than its specific volume V1. As a result, the right-hand side of the equation describing the difference between the temperatures of the air before and after its expansion is negative, that is, free expansion cools the gas. However, this cooling could not be detected by the apparatus used in the Gay-Lussac experiment due to its low sensitivity. In order to overcome this difficulty in the temperature measurement, Joule and Thomson later developed a much more accurate method to examine the variation in temperature during the free expansion of real gases. In their experiment conducted in 1852, Joule and Thomson studied the expansion of a gas through a porous plug in a thermally insulated tube. As the modern version of their apparatus built for demonstration purposes shows, in the experiment a constant flow of gas is maintained along a double piston cylinder that is separated into two compartments by a rigid porous plug. At the initial position of the piston in the left-hand side, the compartment between the piston and the plug has a volume V1, whereas the piston in the right-hand side is exactly at the plug, leaving no space between the plug and the piston. The initial temperature and pressure of the gas in the compartment are denoted by T1 and P1. As constant pressures are applied to both of the pistons, the gas in the left compartment is slowly throttled irreversibly to the right compartment. A force somewhat greater than the force F1 given by the product of the pressure P1 and the cross-sectional area A of the piston is applied to the piston, pushing the gas through the plug into the right compartment. The gas flows slowly enough through the plug so that the gas on the upstream side of the plug remains at the uniform pressure P1, and the gas on the downstream side is at a uniform pressure P2. On the downstream side, a force somewhat smaller than the force F2 given by the pressure P2 times the cross-sectional area A of the piston is applied to the piston so that the gas could only slowly expand. At the final position of the piston on the upstream side there is no space left between the piston and the plug, whereas the compartment on the downstream side has the volume V2. On the upstream side, at a higher pressure is applied to the piston than on the downstream side, and the initial volume is less than the final volume of the expanding gas. The temperatures T1 and T2 of the gas are carefully monitored on either side of the plug. The measurements show that the temperature of the downstream gas in general is different from that of the upstream gas. Depending on the type of the gas, its initial temperature and pressure, and the pressure drop between the compartments, the temperature of the gas can either decrease or increase as it passes through the plug. This temperature change is called the Joule-Thomson effect. For example, the results of the experiment performed with air and hydrogen in the range of atmospheric pressure, where the pressure drop is 1 atmosphere, are the following. For air, the difference between the initial and the final temperatures of the gas is about 1 over 4 degrees Celsius, which means air cools down during the Joule-Thomson expansion. For hydrogen, this difference is equal to about minus 1 over 40 degrees Celsius, that is, hydrogen warms up during its expansion. Because the cylinder is thermally insulated, there is no heat exchange through its walls, that is, the heat Q absorbed or released by the gas is equal to 0. The pressure volume work W done on the piston while the gas is expanding can be written as the difference between the product of the initial pressure P1 and the initial volume V1 and the product of the final pressure P2 and the final volume V2. The first law of thermodynamics tells us that the change in the internal energy U of the expanding gas given by the difference between the final internal energy U2 and its initial internal energy U1 is equal to the heat Q exchanged between the gas and its surroundings plus the pressure volume work W, that is P1 times V1 minus P2 times V2. This gives the equation stating that the internal energy U1 plus the product of the pressure P1 and the volume V1 is equal to the internal energy U2 plus the product of the pressure P2 and the volume V2. Since the enthalpy of a thermodynamic system is defined by the sum of its internal energy U and the product of its pressure P and volume V, the equation tells us that the initial enthalpy H1 of the gas is equal to the enthalpy H2 in its final state. This result shows that the Joule-Thomson expansion of a real gas occurs with constant enthalpy, that is, we talk about an isenthalpic process where the change dH in the enthalpy of the gas is equal to 0. By comparing this finding with the one of the Gay-Lussac experiment where the specific internal energy of a gas during free expansion is constant in the ideal gas approximation, we can see that the specific enthalpy of a gas is constant during the Joule-Thomson expansion in the case of a real gas. It follows from the equation in the left-hand side formulating the first law of thermodynamics that two possible cases exist for such an isenthalpic process. In the first case, the product of the pressure and the specific volume of the gas in its initial state is less than the same product in its final state. This means that the pressure volume work on the piston is done by the gas while it is expanding, and its specific internal energy U must decrease to hold its specific enthalpy constant. As a result, its temperature T decreases as well, that is, the gas cools down during the Joule-Thomson expansion. The second case is the opposite, where the product of the pressure and the specific volume of the gas in its initial state is greater than the same product in its final state. That is, the pressure volume work done on the piston is negative since the piston does work on the gas during the expansion. As a result, the specific internal energy U of the gas increases and the temperature T of the gas increases as well, that is, the gas warms up during the Joule-Thomson expansion. In order to examine the opposite cases or the inversion in the cooling or heating of a real gas during its isenthalpic expansion, we will introduce the Joule-Thomson coefficient of the gas. When determining the differentials of thermodynamic potentials, we wrote the differential of the enthalpy H as the sum of the temperature T times the differential of the entropy S and the volume V times the differential of the pressure P, which vanishes in the isenthalpic process of the Joule-Thomson experiment. Because the entropy S of any thermodynamic system can be expressed as a function of the temperature T and the pressure P at given number of particles n in the system, its differential is equal to its partial derivative with respect to the temperature T at a constant pressure P times the differential of the temperature T, plus its partial derivative with respect to the pressure P at a constant temperature T times the differential of the pressure P. If we substitute this equation into the differential of the enthalpy H, we obtain T times the partial derivative of S with respect to T at constant P times dt, plus the partial derivative of S with respect to P at constant T times dP, plus V times dP. In the first term in the right-hand side of the equation we can replace the partial derivative with the heat capacity Cp of a gas at constant pressure given by its temperature T times the partial derivative of its entropy S with respect to T at a constant pressure P. We could cast the partial derivative in the second term into another form as well when we presented Maxwell relations. By using the mnemonic sentence "the friendly vagabond usually shares his precious gifts," we can reproduce the thermodynamic square which we apply to express the partial derivative of the entropy S at the top left corner of the square in terms of the partial derivative of the volume V at the adjacent corner. If we rotate our position at the corner of the entropy S counterclockwise, then we reach the pressure P at the adjacent corner, which is applied as the independent variable in the derivative of the entropy. A further rotation gives the position of the temperature T, which serves as the constant parameter of the derivative of the entropy with respect to the pressure. For the partial derivative of the volume V in the right-hand side of the relation, we rotate our position at the volume V clockwise and select the temperature T as the independent variable in the derivative of the volume. By rotating our position further, we arrive at the position of the pressure P and use it as the constant parameter of the derivative of the volume with respect to the temperature. Since minus the entropy has the sign opposite to the one of the volume, we write a negative sign in the right-hand side when we express the derivative of the entropy as minus the partial derivative of the volume V with respect to the temperature T at a constant pressure P. By inserting these expressions into the equation describing the differential of the enthalpy H, we can write it as the heat capacity Cp at constant pressure times the differential of the temperature T, minus T times the partial derivative of the volume V with respect to T at a constant pressure P times the differential of P, plus the volume V times the differential of P. Because the thermal expansion coefficient alpha of a gas is given by 1 over the volume V of the gas times the partial derivative of V with respect to the temperature T of the gas at a constant pressure P, which can also be expressed in terms of the molar volume Vm, dH is equal to Cp times dt, plus V times 1 minus T times alpha, times dP. For isenthalpic processes the left-hand side vanishes, and we can formally divide this result by the differential the pressure and write the equation stating that the heat capacity Cp at constant pressure times the partial derivative of the temperature T with respect to the pressure P at a constant enthalpy H, plus the volume V times 1 minus T times the thermal expansion coefficient alpha vanishes. If we define the Joule-Thomson coefficient mu sub Jt of a gas by the partial derivative of its temperature T with respect to its pressure P at a constant enthalpy H, then it can be written as the ratio of the volume V of the gas to its heat capacity Cp at constant pressure, times the product of its temperature T and its thermal expansion coefficient alpha minus 1. This coefficient describing the Joule-Thomson effect for real gases vanishes for an ideal gas since there is no change in the temperature of an ideal gas during its free expansion. The Joule-Thomson coefficient is a function of the temperature and volume of a real gas, and its sign determines whether it cools down or warms up during an isenthalpic expansion. We have introduced the Joule-Thomson coefficient for real gases, which we described by applying either the ideal gas law or the von der Waals approximation. We have already stated this coefficient vanishes for an ideal gas since there is no change in the temperature of the gas during its free expansion. That can immediately be seen if we substitute the ideal gas law into the expression obtained for the Joule-Thomson coefficient. The ideal gas law states that the product of the pressure P and the volume V of the gas is equal to its amount of species N times the gas constant R times the temperature T of the gas. We have expressed the Joule-Thomson coefficient in terms of the thermal expansion coefficient alpha of a gas defined by 1 over the volume V of the gas times the partial derivative of V with respect to the temperature T at a constant pressure P. Then we can replace the volume of the gas in the derivative by applying the equation of state of an ideal gas and compute the derivative, which gives 1 over V, times N times R over P. By substituting the ideal gas law into the right-hand side we obtain 1 over T. As a result, the Joule-Thomson coefficient mu sub Jt given by the ratio of the volume V to the heat capacity Cp at constant pressure, times the temperature T times the heat expansion coefficient alpha minus 1, has a vanishing expression in its parentheses and the coefficient is equal to 0 for an ideal gas. For a von der Waals gas, the equation of state tells us that the sum of the pressure P of the gas and its pressure correction constant A over the square of its molar volume Vm, times the difference between Vm and the volume correction constant B of the gas, is equal to the gas constant R times the temperature T of the gas. The left-hand side of the equation of state can be written as P times Vm, minus P times B, plus A over Vm, minus A times B over Vm squared. If divide this equation by the pressure P, we can express Vm as R times T over P, plus B, plus A over P times Vm, minus A times B over P times Vm squared. Instead of solving this cubic equation for the molar volume Vm, we apply the ideal gas approximation where we write the equation of state in terms of the molar volume Vm of the gas, stating that the product of the pressure P of the gas and its molar volume Vm is equal to the gas constant R times the temperature T of the gas. By using this equation, we can eliminate the molar volume Vm from the last two terms in the right-hand side of the equation obtained for the molar volume Vm. Then Vm can be approximated as R times T over P, plus B, minus A over R times T, plus A times B times P over R squared times T squared. If we insert this result into the definition of the thermal coefficient alpha of the gas expressed in terms of the molar volume Vm and compute the partial derivative of the molar volume with respect to the temperature T at a constant pressure P, then we obtain an approximation of the thermal expansion coefficient given by 1 over Vm, times the quantity of R over P plus A over R times T squared, minus 2 times A times B times P over R squared times T cubed. We substitute this approximation of the thermal expansion coefficient alpha into the expression obtained for the Joule-Thomson coefficient, where the volume V is written as the amount of species N times the molar volume Vm. Then the coefficient can be approximated by N over Cp times the quantity of T times R over P, plus A over R times T, minus 2 times A times B times P over R squared times T squared, minus Vm. Here we write the ratio of the heat capacity Cp to the amount of species N as the molar heat capacity C sub Pm, apply the ideal gas approximation for the molar volume Vm again, and simplify the result. The first and fourth terms immediately cancel out each other, whereas we can add the second and the sixth terms, and the third and the last terms together. As a result, the Joule-Thomson coefficient of a von der Waals gas can be approximated by 1 over the molar heat capacity C sub Pm at constant pressure, times the quantity of 2 times the pressure correction constant A of the gas over the gas constant R times the temperature T of the gas, minus the volume correction constant B of the gas, minus 3 times A times B times the pressure P of the gas over R squared times T squared. This result shows that the Joule-Thomson coefficient of a gas depends both on its physical properties and its temperature and pressure. In many cases the last term of second order in the temperature is dropped from the approximation, showing that the coefficient depends on the temperature but not on the pressure in the first order. Since defined by the derivative of the temperature with respect to the pressure, the coefficient vanishes at the inversion temperature of the gas. In order to study the phenomenon of inversion, we consider the Joule-Thomson coefficient defined by the partial derivative of the temperature T of the expanding gas with respect to its pressure P at a constant enthalpy H, which was also written as the volume V of the gas over its heat capacity Cp at constant pressure, times the temperature T of the gas times its thermal expansion coefficient alpha minus 1. Because it is already approximated in terms of the von der Waals constants A and B of the gas, we cast the coefficient into the form stating that the volume correction constant B over the molar heat capacity C sub Pm of the gas at constant pressure times the square of the temperature T of the gas, times the quantity of 2 times the pressure correction constant A over the gas constant R times B, times T, minus T squared, minus 3 times A times the pressure P of the gas over R squared. By definition, the coefficient is equal to the slope of the isenthalpics in the temperature versus pressure diagram of the gas under the Joule-Thomson expansion. Here we plotted the curves representing the temperature of the gas as a function of its pressure at constant enthalpy for nitrogen. As already mentioned, the definition of the coefficient also shows that for a negative Joule-Thomson coefficient the gas is cooling down during its isenthalpic expansion. If the Joule-Thomson coefficient is positive, then the gas is warming up or reheating during its isenthalpic expansion. This inversion indicates that the thermodynamic states where the coefficient is equal to 0, no cooling or reheating occurs during the isenthalpic expansion of the gas. For a vanishing Joule-Thomson coefficient there is a so-called inversion curve in the temperature versus pressure diagram of the expanding gas, where the inversion temperature TINV is defined by the expression stating that the inversion temperature times the thermal expansion coefficient alpha is equal to 1. This condition involves that the expression in the parentheses of the approximation must be equal to 0. And at the inversion temperature we have the equation stating that the square of the inversion temperature TINV, minus 2 times A over R times B, times TINV, plus 3 times A times P over R squared vanishes. For a given gas with the von der Waals coefficients A and B and for a given pressure P, this equation determines the inversion temperature of the gas in the Joule-Thomson expansion. The inversion curve, that is the points representing the inversion temperatures in the temperature versus pressure diagram, is defined by the maxima of the isenthalpics, as seen in the figure. The diagram also shows that 2 inversion temperatures exist for a given pressure below a maximal pressure, and the difference between them increases with decreasing pressure. The maximum inversion temperature can be obtained from the equation of the inversion temperature evaluated at 0 pressure, which gives 2 times the pressure correction constant A over the gas constant R times the volume correction constant B. If we calculate the temperature where the derivative of the equation of the inversion temperature vanishes and substitute it into the equation, then we can solve it for the pressure. This gives the maximum pressure where the inversion effect exists, which is equal to the pressure correction constant A over 3 times the square of the volume correction constant B. At the same time, the inversion curve separates the region of cooling from the region of reheating represented by the blue and the red areas in the diagram. We note that the regions of cooling and reheating are limited by the region of liquid phase as the purple area shows. If the gas is in the thermodynamic state represented by any point in the blue area, then the gas does work against the molecular forces during its expansion, which reduces its internal energy and the gas cools down. The inverse scenario is where the gas is in a thermodynamic state represented by any point in the red area. Then an external pressure volume work is done on the gas, increasing its internal energy, which usually results in the reheating of the gas. The table shows the maximum inversion temperature for different substances from helium to oxygen, where we can see that this temperature is low for lighter gases like helium or hydrogen, indicating that they have much weaker intermolecular forces than a nitrogen or an oxygen gas. We also note that due to the difference in the pressure in the upstream side and the downstream side of the throttling, the Joule-Thomson expansion is irreversible. There is no thermodynamic equilibrium between the two sides at different pressures, even if the gas flow is slow, that is, the process is not quasi-static. The irreversible expansion of gases are very useful in producing very low temperatures, and it is applied in liquefaction of gases. For example, nitrogen and oxygen with their high maximum inversion temperatures are good candidates for such a procedure since they are easier to liquefy than helium. We already determined the internal energy of real gases in the von der Waals approximation, and now we derive the entropy of a von der Waals gas. When we determine the entropy of an ideal gas, we considered a given amount of gas enclosed in a cylinder with a piston absorbing the infinitesimal amount of heat dq rev from its surroundings at the temperature T in a reversible change of state. In such a process the gas will expand and moves the piston, doing some infinitesimal work dw' on it. We follow the same procedure with a real gas in the von der Waals approximation, but first we consider a special case where the position of the piston is fixed, that is, the volume of the gas is constant and no pressure volume work is done. Then the second law of thermodynamics tells us that the infinitesimal change in the entropy S of the gas absorbing the infinitesimal amount of heat in a reversible process is equal to the ratio of dq rev to the temperature T of the gas. For a constant volume of the gas, that is for isochoric processes, the infinitesimal change of the heat can be written as the mass m of the gas, times the specific heat capacity Cv of the gas at constant volume, times the infinitesimal change in its temperature T. If we formally divide this equation by dt, then we can write the partial derivative of the entropy S with respect to the temperature T at a constant volume V as the mass m times the specific heat capacity Cv at constant volume over the temperature T. In the general case, the gas absorbing the infinitesimal amount of heat is allowed to expand and perform work on the moving piston. Then the entropy of the gas in the cylinder can be written as a function of its temperature T, its volume V, and its number of particles N. As a result, the differential of the entropy S of the given amount of gas can be expressed by its partial derivative with respect to the temperature T at a constant volume V times the differential of the temperature T, plus its partial derivative with respect to the volume V at a constant temperature T times the differential of the volume V. Here the mass m, or equivalently the number of particles N of the gas, is constant. This equation shows that the change of state of the gas in the general case can be split into two processes if we are interested in the change of the entropy of the gas. Because entropy is a state function, it only depends on the initial and the final states of the gas but is independent of the path along which the system is brought from its initial state to its final state. This situation is illustrated in the temperature versus volume diagram of the expanding gas, where the point A represents the initial state of the gas at the initial temperature T1 and the initial volume V1. The final state of the gas is represented by the point B at the final temperature T2 and the final volume V2. If we want to determine the change in the entropy, we can fix the position of the piston and heat the gas so that its temperature can reach the temperature T2 at the state represented by the point C at the initial volume V1. That is, we increase the temperature of the gas in an isochoric process between the states A and C. Then we allow the piston to move such that the warm gas could perform an isothermal expansion between the state C and its final state B, where the volume of the gas is given by V2. The two terms in the right-hand side of the infinitesimal change in the entropy S represent the two processes between the states A and C, and between the states C and B in the diagram. The first term describes the isochoric process, where we already determined the partial derivative of the entropy with respect to the temperature at constant volume. The second term in the right-hand side describes the isothermal process, where we use Maxwell relations to express the partial derivative of the entropy in terms of the partial derivative of a state variable of the gas. By selecting the position of the entropy S at the top left corner of the thermodynamic square, we need to rotate clockwise to the position of the volume V to obtain the independent variable of the partial derivative, and a further clockwise rotation gives the temperature T as the variable held constant in the partial derivative. Thus we have reproduced the partial derivative that we need to express in another form. If we start from the position of the entropy S again but rotate it counterclockwise, we arrive at the position of the pressure P as a dependent variable of the partial derivative. Then we take the partial derivative of the pressure with respect to the temperature T as a further counterclockwise rotation shows. The last counterclockwise rotation selects the volume V as the variable held constant in the partial derivative. Because both the entropy S and the pressure P appear with a negative sign in the thermodynamic square, the partial derivative of the entropy S with respect to the volume V at a constant temperature T is equal to the partial derivative of the pressure P with respect to the temperature T at a constant volume V. Now we use this result for the partial derivative in the second term in the right-hand side in the differential of the entropy. The pressure of a von der Waals gas is equal to the gas constant R times the temperature T, over the difference between the molar volume Vm and the volume correction constant V, minus the pressure correction constant A over the square of Vm. By substituting the pressure P into the right-hand side of the first equation and calculating its partial derivative with respect to T at constant volume, we obtain the ratio of the gas constant R to the difference between the molar volume Vm and the constant B. If we multiply both the numerator and the denominator by the amount of species n, then we can write the right-hand side as n times R over the difference between the volume V and n times B. Here the product of the amount of species n and the gas constant R is equal to the mass m of the gas times its specific gas constant Rs. Now we substitute the expressions obtained for the partial derivatives in the right-hand side of the equation describing the differential of the entropy, and write the infinitesimal change in the entropy of a real gas in the von der Waals approximation as the mass m of the gas times the sum of two terms. The first one is equal to the specific heat capacity Cv of the gas at constant volume over the temperature T of the gas times the differential of T, and the second term is given by the specific gas constant Rs of the gas over the difference between its volume V and its amount of species N times the volume correction constant B of the gas, times the differential of V. In order to determine the change in the entropy of a von der Waals gas brought from the initial thermodynamic state A to the final thermodynamic state B, we need to integrate the differential of the entropy S between the states A and B. As the figure shows, we express ds in a form where the system is brought from the state A and the state C along an isochoric path, and then it is brought from the state C to the B along an isothermal path. In the first term we therefore integrate 1 over the temperature T of the gas along the isochoric path between the initial temperature T1 and the final temperature T2, and in the second term we integrate 1 over the difference between the volume V of the gas and the amount of species N times the volume correction constant B along the isothermal path between the initial volume V1 and the final volume V2. If we choose the initial state A as a zero state, where the entropy S of the system is equal to S not normally set to 0, then the integration gives the entropy S of the gas in its final state B with respect to the reference or the zero state. Let us denote the temperature and the volume of the gas in the zero state by T0 and V0 instead of T1 and V1. We can also drop the index 2 from the temperature and the volume in the final state. By performing the integrations and applying theses notations, we can write the entropy S of a von der Waals gas enclosed in the volume V at the temperature T as the sum of the entropy S0 and the mass m of the gas times the sum of the following terms. The first term is given by the specific heat capacity CV of the gas at constant volume times the natural logarithm of the ratio of the temperature T to the reference temperature T0 in the zero state A, whereas the second term is equal to the specific gas constant Rs of the gas times the natural logarithm of the ratio of the difference between the volume V times and the amount of species N times the volume correction constant B, to the difference between the reference volume V0 and the zero state A and N times B. If we compare this expression with the one derived for an ideal gas, then we see that they differ in the correction terms N times B applied to the volume of the gas and the reference volume. We can also determine the free energy F of a von der Waals gas defined by its internal energy U minus the product of its temperature T and its entropy S. We already calculated the internal energy of a real gas in such an approximation, and found that it is equal to the mass m of the gas times the difference between the specific heat capacity CV of the gas at constant volume times the temperature T of the gas, and A' over the square of the specific volume V of the gas, where A' denotes the ratio of the pressure correction constant A of the gas over the square of the molar mass m sub m of the gas. The specific volume of the gas is just the ratio of its volume to its mass. By substituting this equation and the expression obtained for the entropy into the definition of the free energy, we can write F as the mass m times the quantity of CV times T, minus CV times T times the natural logarithm of T over T0, plus A' over the specific volume V, minus Rs times T times the natural logarithm of the ratio of the difference between the specific volume V and B', to the difference between the specific reference volume V0 and B'. Here B' denotes the volume correction constant B of the gas over the molar mass m sub m of the gas. A comparison with the free energy of an ideal gas shows that the free energy of a real gas in the von der Waals approximation has the correction constant B' for the specific volumes V and V0, and the extra term A' over the specific volume V due to the pressure correction term in the equation of state of the gas. Now we consider an isentropic change of state in the case of a von der Waals gas, that is where the entropy of the gas is constant during the thermodynamic process, or in other words, the change in the entropy of the gas brought from the initial state A to the state B vanishes. Then the terms in the parentheses in the expression derived for the entropy must vanish, where the first term in the right-hand side can be written as the natural logarithm of the ratio of T to T0 raised to the power CV, and the second term is given by the natural logarithm of the ratio of the difference between V and N times B to the difference between V0 and N times B, raised to the power Rs. This sum is equal to the natural logarithm of T to CV times the difference between V and N times B to Rs, over T0 to CV times the difference between V0 and N times B to Rs. Because this expression must vanish, that is the fraction is equal to 1, we obtain an equation stating that T0 to CV times the difference between V0 and N times B to Rs is given by T to CV times the difference between V and N times B to Rs. Here the reference temperature T0 and the reference volume V0 are constants given in the zero state of the system, that is the right-hand side of the equation is constant for any temperature and volume of the gas. Then we conclude that in an adiabatic change of state of real gases, That is, in reversible processes without entropy production, we can state that the temperature T of the gas times the difference between its volume V and its amount of species N times its volume correction constant B, raised to the ratio of the specific gas constant Rs of the gas to its specific heat capacity Cv at constant volume, is constant. We note that this formula reduces to the one obtained for an ideal gas if we set the volume correction constant B of the von der Waals approximation to 0. Indeed, we already derived the condition of the constancy of the product of the temperature T of an ideal gas and its volume V raised to the power gamma minus 1. Here gamma is the adiabatic index of the gas given by the ratio of its specific heat capacity Cp at constant pressure to its specific heat capacity Cv at constant volume. That is, the exponent of the volume V is equal to the difference between Cp and Cv, over Cv. For an ideal gas, we can use Meyer's relation stating that the specific gas constant Rs of the gas is equal to the difference between its specific heat capacities at constant pressure and volume. This is the expression shown above for vanishing B in the ideal gas approximation, which is constant, as expected. In order to describe the deviation of the behavior of real gases from the prediction of the ideal gas law, we introduce the compressibility factor of the gas by modifying the equation of state of an ideal gas. Now we define another quantity called Fugacity, introducing similar modifications in the equations derived for an ideal gas, which gives a better description for the real case. We start with the infinitesimal change in the free enthalpy or the Gibbs potential G of a thermodynamic system given by minus its entropy S times the differential of its temperature T, plus the volume V of the system times the differential of its pressure P. For an isothermal process in a given amount of gas, the first term in the right-hand side vanishes and the infinitesimal change in the free enthalpy reduces to the expression of the product of the volume V and the differential of the pressure P. If we divide this equation by the amount of species N of the gas, we can write the differential of the molar free enthalpy Gm as the molar volume V of the gas M times the differential of the pressure P. We consider the isothermal change of state of an ideal gas between the state A at the pressure P1 and the state B at the pressure P2, where the ideal gas law states that the pressure P of the gas times its molar volume Vm is equal to the gas constant R times the temperature T of the gas. Then the change in the molar free enthalpy Gm of the gas in this process is given by the integral of the molar volume Vm of the gas with respect to the pressure P from the initial pressure P1 to the final pressure P2. By substituting the ideal gas law into the integral, we can write the right-hand side of the equation as R times T, times the integral of 1 over P with respect to P from P1 to P2. If we perform the integration, then the difference in the molar Gibbs potential between the final state B and the initial state A can be expressed by R times T times the natural logarithm of the ratio of P2 to P1. As in the case of entropy and free energy, the initial state A or any other state can be chosen as a reference or zero state with the reference value of G0 sub m at the pressure P0. Then the molar free enthalpy Gm of an ideal gas at the temperature T and the pressure P is given by the reference value of G0 sub m plus the gas constant R times the temperature T, times the natural logarithm of the ratio of the pressure P to the reference pressure P0. The deviation of the behavior of a real gas from the ideal gas law with respect to the molar Gibbs potential of the gas can be described and measured by introducing a new quantity F instead of the pressure P of the gas called the fugacity of the real gas. The fugacity F is the effective pressure of the gas, which gives the measured value of the free enthalpy G or the molar free enthalpy Gm of a real gas. We note that fugacity can also be introduced by using the chemical potential of the gas instead of its molar free enthalpy, since the multiplication factor between them is just the Avogadro constant. The relation between the effective pressure F and the measured pressure P is described by the formula stating that the fugacity F is equal to the product of a fudge factor phi and the pressure P. The multiplication factor phi is called fugacity coefficient, and it is a function of the state variables of the gas. Let us suppose that the effective pressure in the state A is described by the fugacity F1, whereas F2 denotes the fugacity of the real gas in the state B. Then the change in the molar Gibbs potential Gm of the gas brought from the state A to the state B in an isothermal process at the temperature T is given by the difference between the gas constant R times the temperature T, times the natural logarithm of the ratio of the fugacity F2 to the reference pressure P0, and R times T times the natural logarithm of the ratio of the fugacity F1 to the reference pressure P0. Here the right-hand side is equal to R times T times the natural logarithm of the ratio of F2 to F1. Now we can compare the change in the free enthalpy computed for the ideal gas law and the one measured for a real gas. For an ideal gas, we can write the integral of the molar volume of an ideal gas with respect to the pressure P from the pressure P1 to the pressure P2 as R times T times the natural logarithm of the ratio of the pressure P2 to the pressure P1. In the case of a real gas, the same integral of the molar volume of the real gas is given by R times T times the natural logarithm of the ratio of the fugacity F2 to the fugacity F1. We can use these expressions to integrate the difference between the molar volumes of a real gas and an ideal gas with respect to the pressure P from the pressure P1 in the state A to the pressure P2 in the state B, which can be written as the gas constant R times the temperature T, times the natural logarithm of the fugacity F2 of the real gas in the state B to the fugacity F1 of the real gas in the state A, minus R times T times the natural logarithm of the pressure P2 to the pressure P1. The right-hand side is equal to R times T times the natural logarithm of the ratio of F2 divided by P2 to F1 divided by P1, where we can express the logarithm of the fraction as 1 over R times T, times the integral of the difference between the molar volumes of a real gas and an ideal gas with respect to the pressure P from the pressure P1 to the pressure P2. Let us suppose that the pressure P1 in the initial state A tends to 0, and we can use the ideal gas approximation to describe the behavior of the real gas in its initial state. In this case, the fugacity, that is the effective pressure, approaches the pressure, and the fugacity coefficient phi becomes 1, that is the ratio of the fugacity F1 to the pressure P1 in the initial state A tends to 1. Then the left-hand side of the equation is equal to the natural logarithm of the ratio of the fugacity F2 to the pressure P2, where we integrate from 0 pressure in the right-hand side. Since the fugacity F2 is equal to phi times the pressure P2, the ratio in the logarithm can be written as the fugacity coefficient phi, and we can drop the index 2 from the pressure in the final state. As a result, we have an equation that defines a quantity measuring the deviation of the behavior of a real gas from the ideal gas law with respect to its molar enthalpy in an isothermal process in terms of the difference between the molar volumes of a real and an ideal gas. Now we can apply the ideal gas law, telling us that the pressure P of an ideal gas times its molar volume V sub m ideal is equal to the gas constant R times the temperature T of the gas, and the real gas law for the same pressure and temperature, stating that the pressure times the molar volume V sub m real of the real gas is equal to the compressibility factor Z of the real gas times R times T. Then 1 over R times T, times the difference between V sub m real and V sub m ideal can be expressed as Z minus 1 over P, and the natural logarithm of the fugacity coefficient phi of a real gas with the compressibility factor Z at the temperature T and the pressure P, is equal to the integral of the compressibility factor Z minus 1 over the pressure P with respect to the pressure from 0 to the pressure P. Here we indicated that the compressibility factor of a real gas depends on its temperature and pressure, and if Z is a known function of the state variables, then the fugacity coefficient of the gas can be derived from the integral. We already saw that the compressibility factor Z is a universal function of the reduced temperature and the reduced pressure for any real gas, and its value for given reduced temperature and reduced pressure can be determined by using generalized compressibility charts. At the same time, the differential of the pressure P over the pressure P is equal to the differential of the reduced pressure PR over the reduced pressure PR, which indicates that the fugacity coefficient expressed in terms of the reduced temperature and the reduced pressure is also universal for any real gas. Then we can plot generalized fugacity coefficient charts for real gases, for example these chart compiled for pure substances. As in the case of the compressibility charts, we can see different plots for different ranges of the reduced pressure of the substances. In the first chart, the fugacity coefficient phi is plotted as a function of the reduced pressure PR from 0 to 0.5 at constant reduced temperatures between 0.5 and 1.6. In the second chart, the range of the reduced pressure is between 0.1 and 50 at the constant reduced temperatures from 0.65 to 15. Here the blue curve represents the saturation line separating the phase of liquid saturated vapor from the phase of unsaturated vapor for all substances. The parts of the curves represented by dashed lines in the first chart are in the range under the saturation line. The charts show that at very low pressures the fugacity coefficient is close to 1, as the ideal gas approximation still gives a reasonable description of the behavior of real gases. In this range the effective pressure is essentially the same as the real pressure of the gas used in the calculation of its molar free enthalpy. With increasing pressure, the fugacity coefficient drops to a minimal value for a given reduced temperature, that is, the effective pressure is less than the real pressure of the gas. The minimum value of phi increases with increasing reduced temperature. Above a given reduced pressure, depending on the reduced temperature, the fugacity coefficient starts to increase and it will surpass 1 at some point. The higher the reduced temperature is, the less the reduced pressure at which phi becomes greater than 1. In that region the effective pressure becomes greater than the real pressure of the gas when we determine its molar Gibbs potential. We finished the discussion on the fugacity of real gases with the approximation of the fugacity coefficient of a von der Waals gas, and we also give some remarks on the enthalpy of real gases. We saw that the compressibility factor Z of a real gas can be expressed as the pressure P of the gas times its molar volume Vm over the gas constant R times the temperature T of the gas. If we substitute the von der Waals equation into the pressure in the fraction, the right-hand side becomes Vm over the difference between Vm and the volume correction constant B, minus the pressure correction constant A over R times T times Vm. Here we introduce the notations capital A for A over R squared times T squared, capital B for B over R times T, and H for B over Vm, which is similar to the conventional notations applied for the modified versions of the von der Waals equation of state. By using this notation, the compressibility factor of the von der Waals gas can be written as 1 over 1 minus H, minus capital A over capital B, times the pressure P. Although the formula obtained for Z has a simple form, we need to express the compressibility factor in terms of the pressure and the temperature in the calculation of the fugacity coefficient. If we write the molar volume Vm of a von der Waals gas as the compressibility factor Z of the gas times the gas constant R times the temperature T of the gas over its pressure P, we can use the so-called ideal gas approximation of the molar volume which we introduced in the discussion on the Joule-Thomson effect. In such an approximation the molar volume of a von der Waals gas is written as R times T over P, plus the volume correction constant B of the gas, minus the pressure correction constant A of the gas over R times T, plus A times B times P over R squared times T squared. Then the ratio of Z minus 1 to P can be approximated by 1 over R times T, times the quantity of B minus A over R times T, plus A times B times P over R squared times T squared. Here we can apply the notation introduced above, and write the right-hand side as capital B minus capital A, plus capital A times capital B times the pressure P. Because we need to integrate the left-hand side of this approximation to obtain the logarithm of the fugacity coefficient phi, we can insert its right-hand side into the integral and perform the integration. As a result, the logarithm of phi is given by the difference between capital B and capital A times the pressure P, plus capital A times capital B over 2, times the square of the pressure P. Here the second term represents a second-order contribution of the pressure in this approximation. Since we have already determined the entropy and the free enthalpy of real gases, we also derive an expression for their enthalpy. The infinitesimal change in the enthalpy H of a thermodynamic system is equal to the temperature T of the system times the differential of its entropy S, plus the volume V of the system times the differential of its pressure P. In the case of isothermal processes we can formally divide this equation by dP, and write the partial derivative of the enthalpy H with respect to the pressure P at a constant temperature T as the temperature T times the partial derivative of the entropy S with respect to P at constant temperature, plus the volume V. Here we use the Maxwell relations encoded in the thermodynamic square to cast the partial derivative in the right-hand side into a more convenient form. By selecting the position of the entropy S at the top left corner of the thermodynamic square, we need to rotate counterclockwise to the position of the pressure P to obtain the independent variable of the partial derivative, and a further counterclockwise rotation gives the temperature T as the variable held constant in the partial derivative. Thus we have reproduced the partial derivative that we need to express in another form. If we start from the position of the entropy S again but rotate it clockwise, we arrive at the position of the volume V as a dependent variable of the partial derivative. Then we take the partial derivative of the volume with respect to the temperature T as a further clockwise rotation shows. The last clockwise rotation selects the pressure P as the variable held constant in the partial derivative. Because only the entropy S is the dependent variable that appears with a negative sign in the thermodynamic square, we apply a negative sign for S, and state that minus the partial derivative of the entropy S with respect to the pressure P at a constant temperature T is given by the partial derivative of the volume V with respect to the temperature T at a constant pressure P, which can be inserted into the right-hand side of the equation. Then the differential of the enthalpy H is equal to the difference between the volume V and the temperature T times the partial derivative of V with respect to T at constant pressure, times the differential of the pressure P. This expression can be used to determine the residual enthalpy of the real gas in an isothermal process. Residual properties quantify the deviation of a real gas from the behavior of an ideal gas at the same temperature and pressure. That is, residual enthalpy is the difference between the actual enthalpy of a real gas and that of an ideal gas at the same temperature and pressure. The residual free enthalpy characterized by the fugacity of the real gas or the residual entropy can be defined in the same way. Because the molar enthalpy of a system brought from the zero state to an arbitrary thermodynamic state is given by the integral of hm along an isothermal path between these states, the result can be substituted into this integral and we integrate the difference between the molar volume Vm and the temperature T times the partial derivative of Vm with respect to T at constant pressure. The integral is performed with respect to the pressure P from zero pressure in the zero state to the pressure P in the actual state. If we substitute this result into the definition of the residual enthalpy of a real gas, we obtain the difference of two terms in the right-hand side calculated for the real gas and the ideal gas, where n denotes the amount of species of the gas. In the first term given for the real gas, we can write the molar volume Vm in the integral as the compressibility factor Z times the gas constant R times the temperature T over the pressure P. In the second term given for the ideal gas, the compressibility factor is equal to 1. If we compute the partial derivative in the integrals, we can see that the second term vanishes and we can state that in an isothermal process the residual HR of n mole real gas at a given temperature T and pressure P is equal to minus the amount of species n times the gas constant R times T squared, times the integral of the partial derivative of the compressibility factor Z of the gas with respect to its temperature T at constant pressure times 1 over the pressure P. The integral is computed with respect to the pressure P from zero pressure to the actual pressure P of the gas. Accurate experimental data can be used in evaluating this expression, but general compressibility charts also provide the values of the compressibility factor of real gases for given reduced temperature and reduced pressure. We saw that the von der Waals equation was introduced to achieve a better description of the behavior of real gases than the one provided by the ideal gas law. This equation of state is derived from the von der Waals approximation characterizing the opposite intermolecular forces by a long-range attractive and a short-range repulsive potential, as already presented in the plot of the net potential energy of the von der Waals forces versus the molecular distance r. Based on this approximation, von der Waals constructed a cubic equation in terms of the volume of gas, where the pressure P of the gas is equal to the gas constant R times the temperature T of the gas over the difference between the molar volume Vm of the gas and its volume correction constant V, minus the pressure correction constant A over the square of Vm. The correction constants A and B are the parameters in the equation of state specific for any substance modeled as a von der Waals gas or fluid. The first term in the right-hand side of the equation of state is responsible for the volume correction for the volume excluded by the molecules due to the repulsive intermolecular forces, which is also called the repulsion term of the von der Waals equation. The role of the second term is the correction in pressure due to the attractive intermolecular forces, and it's also known as attraction term. As a result, the pressure in the equation of state can formally be written as the sum of two terms, the pressure attributed to the repulsive intermolecular forces and a negative pressure correction term due to the attractive intermolecular forces. In this model, the repulsion term depends on both the temperature T and the molar volume Vm of the gas with the volume correction constant V, whereas the attraction term depends on Vm and the pressure correction constant A. Because the von der Waals approximation describes the behavior of real gases only with a limited accuracy, several modifications were constructed to improve the von der Waals equation. Here we present some of the most popular examples proposed over the last few decades, which can be divided into three groups. The first group consists of those equations of state where the pressure correction is improved in the attraction term of the von der Waals equation. In these modifications, the denominator of the attraction term remains quadratic in the molar volume. That is, the improved equations of state remain cubic in the volume of the substance. In the case of the second group, the volume correction formula is modified in the repulsion term of the von der Waals equation, which results in non-cubic equations of state. Evidently, those improved equations of states belong to the third group where both the pressure correction and the volume correction are modified. That is, there are some improvements in both the attraction term and the repulsion term of the von der Waals equation. We start with the short overview on several cubic equations of state which are frequently used in thermodynamic calculations. The first cubic equation we will present is the Redlich-Kwong equation of state, where the attraction term also depends on the temperature and the pressure correction involves the volume correction constant. Then we will talk about the Soave-Redlich-Kwong equation of state, where the temperature dependence of the attraction term has a more general form, and the acentric parameter omega is introduced to accommodate the effects of the deviation from the spherical symmetry of the molecules interacting each other in the real gas, vapor or liquid. The next equation of state we will present is the Peng-Robinson equation, which follows a similar strategy by keeping the acentric parameter but applying the volume correction parameter more extensively in the attraction term. We will also consider its improvement called the Peng-Robinson-Strijek-Vera equation of state, where an adjustable empirical parameter kappa 1 specific for substances with some temperature dependence is introduced in the attraction term. The last cubic equation of state we talk about is the Patel-Teja equation, where a third parameter C is introduced in the attraction term of the equation, providing substance-specific critical compressibility factors based on experimental data. Then we will present three non-cubic equations of state where only the repulsion term is modified, starting with Guggenheim's equation of state. In this equation, a more accurate model is provided for the hard sphere interactions between molecules, and some experimental data are applied in the thermodynamic calculations with the repulsion term as well. The next non-cubic equation of state we will consider is the Carnahan-Starling equation, where a more accurate representation of the hard sphere interactions is achieved by applying the virial expansion of the repulsion term with a closed formula for the expansion coefficients. The last equation of state in the second group we talk about is the Bublik equation of state, where the hard sphere geometries of the interacting molecules are generalized by using non-sphericity parameters in the attraction term. Finally, we will present three examples in the third group, starting with the equation of state derived from the simplified perturbed hard chain theory, which still applies the Carnahan-Starling approximation in the repulsion term and uses a theory unifying polymer solution theories and the perturbed hard sphere theory to model the molecular interactions in the attraction term. Then we will talk about the Christoforacos Heilig-Franck equation of state, providing a generalized expression of the Carnahan-Starling equation for the repulsion term and applying a square well potential model for molecular interactions in the attraction term. The last equation we will consider here is the Dieter's equation of state, which still uses the Carnahan-Starling approximation in the repulsion term but applies a semi-empirical description of the square well potential model in the attraction term. In order to be able to compare the different equations of state that we will present here, we will introduce some conventional notation frequently used in this context. We derive several relations between the von der Waals constants A and B and the critical constants of a gas, and we will use two of them here. The first relation tells us that the pressure correction constant A can be written as 27 times the square of the volume correction constant B, times the critical pressure Pc of the gas, and the second one states that A is given by 27 times B over 8, times the gas constant R times the critical temperature Tc of the gas. If we express the constant B from the first relation and substitute it into the square of the second one, then we obtain A in terms of the critical constants, which can be inserted into the first relation to express B in terms of the critical constants. As a result, the von der Waals constants A and B can be written as omega A times R squared times Tc squared over Pc, and omega B times R times Tc over Pc, where the constants omega A and omega B are equal to 27 over 64 and 1 over 8, respectively. Now we start with a cubic equation of state introduced by Redlich and Kwong in 1949 to improve the von der Waals equation, which is an empiric formula with a modified attraction term. In this equation of state, the denominator of the second term correcting the pressure becomes temperature dependent, and it is given by Vm times the sum of Vm and B, times the temperature T raised to the power 1 over 2. The parameters of Redlich-Kwong equation of state are still the pressure and volume correction constants A and B of the gas, and they can be expressed in terms of the critical constants of the gas from the vanishing first and second order derivatives of the pressure with respect to the molar volume evaluated in the critical point of the gas. As a result, the pressure correction constant A is given by omega A times R squared times Tc raised to the power 5 over 2, over Pc, whereas the volume correction constant can be written as omega B times R times Tc over Pc with the constants omega A and omega B that are equal to 0.42748 and 0.08664, respectively. These numbers are values of the fractions containing square roots of integers that appear in the solution of the equations obtained from the vanishing first and second order derivatives. The critical compressibility factor Zc of the gas can also be determined from these equations supplemented with the definition of Zc. For the Redlich-Kwong equation, Zc is given by 1 over 3, which is a value closer to the typical values of Zc for real gases than 3 over 8 obtained from the von der Waals equation, overestimating them. The compressibility factor Z of a gas can be derived in terms of its state variables from the improved equation of state as well, and expressed by 1 over 1 minus h, minus capital A squared over capital B, times h over 1 plus h, where the square of capital A is defined by A over R squared times T to 5 over 2, capital B refers to B over R times T, and h simply denotes B over Vm. Redlich and Kwong compared the prediction of the modified equation of state with the one of the von der Waals equation for the measured data of the compressibility factor of ethane as a function of its reduced pressure, demonstrating the improvement produced by the temperature-dependent pressure correction in the equation. By applying the equation obtained for the compressibility factor, the natural logarithm of the fugacity coefficient phi of a real gas can also be calculated, and it can be written in the form Z-1, minus the natural logarithm of the difference between z and B times p, minus A squared over B, times the natural logarithm of 1 plus B times p over z. The Redlich-Kwong equation of state allows one to reliably calculate the critical properties for various substances, predict both vapor and liquid properties, and describe high-pressure phase equilibria for both pure gases and binary mixtures. The Soave-Redlich-Kwong equation of state was introduced in 1972, when Soave suggested a more general temperature-dependent attraction term in the Redlich-Kwong equation. Instead of the temperature T raised to the power 1 over 2 in the denominator, he applied a temperature-dependent function called alpha function or cohesion function in the numerator with a third parameter omega besides the correction constants A and B. This parameter is called eccentric factor, describing the deviation of the reduced vapor pressure of a substance from its pressure in fluid phase, and it is associated with the shape and polarity of the molecules, measuring their deviation from spherical symmetry. The alpha function is derived from the fit of the experimental values of the vapor pressure of pure substances, where the square root of alpha is plotted against the square root of the reduced temperature measured for a number of hydrocarbons. Because the data points for each substance with given critical constants form almost straight lines passing through the point where Tr and alpha are equal to 1, Soave used a linear approximation. He expressed alpha raised to the power 1 over 2 by 1 plus the slope m of the line obtained for a given substance times 1 minus its reduced temperature Tr raised to the power 1 over 2. By applying the definition of the eccentric factor omega, stating that the reduced saturation vapor pressure at the reduced temperature of 0.7 is equal to 10 to the power minus 1 minus omega, the alpha function can be evaluated at the same reduced temperature. Because the straight lines must pass through the point given by this reduced temperature and the corresponding value of alpha, the slope m can be determined as a quadratic polynomial of omega. Here the pressure and volume correction constants A and B expressed in terms of the critical constants have the same form as in the case of the von der Waals equation of state, but the constants omega A and omega B are equal to those of the Redlich-Kwong equation of state. The critical compressibility factor is also the same, that is Zc is given by 1 over 3. The compressibility factor as a function of the state variables is obtained by solving the cubic equation of Z derived from the Soave-Redlich-Kwong equation of state, which states that Z cubed minus Z squared plus the quantity of A minus B minus B squared, times Z, minus A times B, is equal to 0, where A denotes A times alpha times P over A squared times T squared and B is defined by B times P over A times T. In the general case, this equation has three distinct roots where the maximum of the roots gives a compressibility factor of the substance in the vapor phase and the minimum corresponds to a value of Z in the liquid phase of the substance. The same cubic equation of Z can also be given for the Redlich-Kwong equation of state, but the definitions of A and B are different. As a result, the fugacity differs from the one obtained for the Redlich-Kwong equation, and the natural logarithm of the fugacity coefficient phi of the gas is given by Z minus 1, plus the natural logarithm of the difference between Z and B, minus A over B, times the natural logarithm of 1 plus B over Z. Since the Soave-Redlich-Kwong equation is based on the fitting of the measured vapor-liquid curve, it is able to describe the phase behavior in the critical region better than the Redlich-Kwong equation of state. The modification introduced by Soave also improved the accuracy in the critical properties and the calculations of phase equilibria of hydrocarbons compared with the measurements. The next cubic equation of state is the Peng-Robinson equation, introduced in 1976 to improve the Soave-Redlich-Kwong equation of state, where the denominator of the attraction term is replaced with the molar volume Vm times the sum of Vm and the volume correction constant B, plus B times the difference between Vm and B. The alpha function still has the same form, but the polynomial of the eccentric factor omega in the slope parameter has different coefficients, which is denoted by kappa instead of m. As a result, in the correction constants A and B expressed in terms of the critical constants of gas, the constants omega A and omega B become 0.45724 and 0.07780, respectively. The cubic equation of the compressibility factor Z of the substances derived from the Peng-Robinson equations of state tells us that Z cubed, minus 1 minus B times Z squared, plus the product of the quantity of A minus 2 times B minus 3 times B squared and Z, minus the quantity of A times B minus B squared minus B cubed is equal to 0. Here the definitions of the quantities A and B are the same as the ones for the Soave-Redlich-Kwong equation. As already mentioned, the maximum and the minimum of the roots of this cubic equation generally corresponds compressibility factors of the substance in its vapor phase and its liquid phase, respectively. The critical compressibility factor ZC derived from this equation in the critical point is equal to 0.307401, which is closer to the values measured for real gases than the value predicted by the Redlich-Kwong equation of state and Soves's improved version of it. The natural logarithm of the Fugacity coefficient phi is given by z-1, minus the natural logarithm of the difference between z and capital B, plus capital A over 2 times square root 2 times capital B, times the natural logarithm of the difference between z and 1 minus square root 2 times capital B over the sum of z and 1 plus square root 2 times capital B. The Peng-Robinson equation generally performs better in predicting liquid densities, especially for nonpolar substances, compared to the Soave equation. In 1986, Strijak and Vera proposed the following modified version of the Peng-Robinson equation of state to extend the range of its applicability to polar substances. Their equation of state still has the same form as the one introduced by Peng and Robinson, but the square root of the alpha function in the attraction term is defined by kappa naught, plus kappa 1 times 1 plus the reduced temperature Tr raised to the power 1 over 2, times 0.7 minus Tr. In this equation, kappa naught denotes a cubic polynomial of the eccentric factor omega, and kappa 1 is an adjustable empirical parameter for each pure substance depending on the reduced temperature Tr. Strijak and Vera provided a table for the values of the parameter kappa 1 for several pure substances that apply at low reduced temperature up to the critical point. If kappa 1 is set to 0 at the reduced temperatures above 0.7, then the equation of state produces better results. The values of omega A and omega B for the modified Peng-Robinson equation are the same as those derived for the original equation of state, but the pressure correction factor A is different due to the application of an improved alpha function. Since the Peng-Robinson equation and the modified equation introduced by Strijak and Vera has the same form, the cubic equation for the compressibility factor and the expression of the natural logarithm of the Fugacity coefficient have the same forms as well. However, the explicit form of the alpha function in the definition of capital A differs in the original and the improved version of the equation of state, which produces different results in the thermodynamic calculations. Strijak and Vera illustrated the improvement in these results by comparing the deviations in vapor pressure calculated with the Peng-Robinson equation of state seen in the left-hand plot and with their modified equation of state seen in the right-hand plot. The difference between the calculated vapor pressure and the experimental data for several substances given in percentages versus their reduced temperature shows that the improved equation of state produces at least one order smaller deviations in vapor pressure than the original equation of state. Another form improving the Peng-Robinson equation is the Patel-Teja equation of state proposed in 1982, where a third parameter C was introduced in the pressure correction term of the equation of state. The square root of the alpha function is defined by 1 plus a factor f times 1 minus the reduced temperature Tr raised to the power 1 over 2, where f is an empirical parameter specific for the given substance and it is determined by minimizing errors between experimental saturated vapor pressures and those derived from the equation of state. Patel and Teja calculated the factor f for several substances and correlated its value to the eccentric factor for nonpolar substances, yielding a quadratic equation in terms of omega. Similarly to the correction constants A and B, the parameter C can also be expressed in terms of the critical constants where the factors omega A, omega B and omega C are determined by applying the same procedure minimizing the error in the saturated vapor pressure as the one applied for the factor F. In this procedure, instead of predicting a fixed value for the critical compressibility factor ZC, it is considered as a substance-specific empirical parameter denoted eta C, that can be adjusted with the error minimizing process and correlated to the eccentric factor for nonpolar substances. Then the parameter eta C can also be expressed as a quadratic polynomial of omega. As a result of the error minimization, the following equations are obtained and used to determine omega A, omega B, and omega C. In the first equation, omega C is expressed by 1 minus eta C, whereas the second equation states that omega B cubed, plus 2 minus 3 times eta C times omega B squared, plus eta C cubed times omega B, minus eta C cubed is equal to 0. The smallest positive root of this cubic equation gives the factor omega B, which can be substituted into the third equation expressing the factor omega A by 3 times eta C squared, plus 3 times 1 minus 2 times eta C times omega B, plus omega B squared, plus 1 minus 3 times eta C. The Patel-Teja equation of state gives a cubic equation for the compressibility factor Z that states that Z cubed, minus 1 minus capital C times Z squared, plus the quantity of capital A minus capital B minus capital C minus 2 times capital B times capital C minus capital B squared, times Z, minus the quantity of capital A times capital B minus capital B times capital C minus capital B squared times capital C is equal to 0. Here the quantities A and B have the same definitions as in the case of the Soave-Redlich-Kwong and the Peng-Robinson equations, whereas C is defined by the constant C times the pressure P over the gas constant R times the temperature T. This cubic equation has 1 to 3 positive real roots depending upon the number of phases in the system. If a vapor and liquid phase of the substance are present, the smallest root represents the liquid's compressibility factor while the largest root is that of the vapor. The Patel-Teja equation of state provides better results to correlate and predict the thermodynamic properties of many pure substances. In general, the cubic equations of state with 3 parameters have a substance-dependent empirical critical compressibility factor, and as a consequence, they are superior to 2-parameter equations of state in describing liquid densities. Now we present some of the frequently used modifications of the von der Waals equation which results in non-cubic equations of state for real gases or liquids. The motivation of such modifications is based on the fact that the attraction term in the von der Waals equation providing the contribution of the intermolecular forces to the internal energy of substances, while inaccurate at low densities is a useful approximation at high densities. At the same time, the repulsion term gives an inaccurate contribution to the entropy of fluids and real gases, except at densities so low that interactions between 3 or more molecules are negligible. Then without modifying the attraction term in the equation of state, a better approximation can be introduced in its repulsion term at high densities by applying an improved model of non-interacting rigid spheres for the molecules in substances. The first example of such equations of state was proposed by Guggenheim in 1965, where the denominator in the repulsion term of the equation is written as the molar volume Vm of the gas times 1 minus y raised to the power 4. The parameter y is defined by the volume correction constant B over 4 times Vm, and it is also known as packing fraction since B determines the volume excluded by a given molecule. Guggenheim calculated the virial expansion of the von der Waals equation with the pressure correction constant set to 0, where the multiplier factor of the molar volume can be written as 1 minus 4 times y, and obtained a polynomial expression for the packing fraction y. The same expansion of his modified version of the equation of state with the pressure correction constant set to 0 gave another polynomial of y. The comparison of the expanded equations with the accurate virial expansion obtained in statistical mechanics indicates that the Guggenheim equation of state produces a better approximation of the accurate virial expansion than the von der Waals equation. In the general case, the pressure correction constant A is not 0, and the assumption of the fixed ratio of A to B is also used at the triple point of the substance where all the 3 states of matter can coexist. If we multiply the equation of state by the molar volume Vm and divide it by the product of the gas constant R and the temperature T, then the ratio of the pressure P times Vm to R times T becomes negligible at the triple point compared to the other terms in the equation. As a result, 1 minus y at the triple point raised to the power minus 4 is equal to the volume correction constant A divided by the product of the molar volume V at the triple point, the gas constant R, and the temperature T at the triple point. Because the volume correction constant A is directly related to the cohesive energy of the liquid, which is the energy required to overcome intermolecular attractions during vaporization, it is proportional to the amount of energy required to vaporize 1 mole of a liquid at a given temperature and pressure. Then the right-hand side can be expressed as the molar energy UM of evaporation of the liquid over the gas constant R times the temperature T. The experimental value of this ratio is equal to 8.56 for argon, which is used to determine YT, that is the value of the volume correction constant V. At the same time, A also appears in this relation, setting the fraction A over B to a constant. As a result, we obtain the values 0.4963 and 0.18727 for omega A and omega B, respectively. Guggenheim determined several quantities by using his modified equation of state and compared them with the figures obtained from the von der Waals equation and the experimental data for argon. In this table we show the critical compressibility factor Zc, and the ratio of the critical pressure Pc times the molar volume Vm in the liquid phase to the gas constant R times the critical temperature T. For the von der Waals approximation, Zc is 3 over 8, that is 0.375, whereas the Guggenheim equation of state produces the value 0.361, which is somewhat closer to the measured value 0.29 for argon. The ratio of Pc times V sub ml to R times Tc shows a significant improvement from the value 0.141 predicted by the von der Waals equation to the value 0.109 compared with the experimental data given by 0.108. The second table compares the ratios of temperatures and volumes evaluated for the 2 equations of state with the measured values for argon. By considering the ratio of the volume V in the liquid phase to the critical volume Vc of argon, we see that the von der Waals equation performs better than its modified version. For the experimental value 0.374, the von der Waals equation predicts 0.377, whereas the Guggenheim equation gives only 0.303. This poor performance can be seen for any quantity containing the critical volume, due to the fact that the partial derivative of the volume with respect to the pressure at constant temperature diverges at the critical point. As a result, even a small inaccuracy in the isothermals in the pressure-volume diagram affecting the critical pressure only slightly, has a considerable effect on the predicted value of the critical volume. However, the ratio of the temperature at the triple point to the critical temperature is equal to 0.528 for the Guggenheim equation, which is very close to the measured value 0.557 in comparison with the value 0.350 predicted by the von der Waals equation. The next non-cubic equation of state was introduced by Carnahan and Starling in 1969 with the aim to improve the model of the hard sphere interactions in real gases and fluids. The multiplication factor describing the repulsive effect of the hard sphere model in the first term of their equation of state is given by the ratio of the polynomial 1 plus y squared minus y cubed, to 1 minus y raised to the power 3. Here y still represents the packing fraction of the molecules. This expression for the volume correction term is derived from the approximation of the virial coefficients in the expansion of the compressibility factor also used for the Guggenheim equation. As the expansion in the exact form shows, z can be approximated by the following polynomial with integer coefficients: 1 plus 4 times y, plus 10 times y squared, plus 18 times y cubed, plus 28 times y to 4, plus 40 times y to 5 and so on. Carnahan and Starling wrote this infinite sum as 1 plus the sum of the multiplication factor n squared plus n minus 2, times y raised to the power n minus 1 from n equals 2 to infinity, which is equal to 1 plus the sum of the multiplication factor n squared plus 3 times n, times y to n from n equals 0 to infinity. Because the infinite sums in the right-hand side are derivative forms of the geometric series, they can be expressed in closed form. By manipulating the geometric series, the result for the compressibility factor z can be written as the fraction of the polynomials of y in the modified equation of state. In the Carnahan and Starling equation, the relations between the pressure and volume correction constant A and B, and the critical constants are still described by the same multiplication factor omega A and omega B as in the case of Guggenheim's equation. Nevertheless, the modified equation predicts the value 0.35896 for the critical compressibility factor Zc, which is less than the value obtained from the Guggenheim equation of state, that is closer to the range of the values measured for real gases. This plot shows the compressibility factor for A equals 0, that is for the repulsive part of the von der Waals and the Carnahan and Starling equations of state versus the packing fraction y. The comparison between the curves and the molecular dynamics data represented by the black rectangles illustrates the improvement in the description of the repulsive intermolecular forces in real substances produced by the Carnahan and Starling equation. As a result, the critical constants predicted by this modified equation of state do not differ appreciably from that obtained using the virial expansion in statistical mechanics. The third non-cubic equation of state we present here is proposed by Bublik in 1981, but we show it in a form introduced by Sveda and Kohler 2 years later. The repulsion term in this equation still has the denominator 1 minus y raised to the power 3 as in the case of the previous equation of state, but the cubic polynomial in its numerator contains multiplication factors depending on a parameter alpha. This parameter describes the deviation of the gas molecules from spherical symmetry, where they are treated as hard convex bodies and their repulsive interactions between each other, and alpha is given by the mean radius r star of a hard convex body times its surface area s star over 3 times its volume v star. By definition, alpha is equal to 1 for simple hard spheres, which gives the Carnahan and Starling equation of state. In the hard convex body model, the parameters r star, s star, and v star are determined from the molecular geometry for a given gas or fluid. Different procedures are applied to construct hard convex bodies or shapes for molecules in fluids and N-alkanes. In the case of fluid molecules, the hard convex shape is divided into two parts, a polyhedron or polygon called hard core with several interaction centers determining the appearance of the molecule for its neighbors. The other part is added on the top of this geometric figure as a smoothing hard layer with equal thickness that covers the hard core with its all corners and edges completely. In the case of N-alkanes, the shape of the molecules are assumed to correspond to hard spherocylinders, which look shorter and thicker for curled alkanes and longer and thinner for less curled alkanes. As an illustration, we plotted the reduced temperature versus the reduced density for the vapor-liquid equilibrium of ethane derived from the von der Waals and the Bublik equations of state, where the comparison with the experimental data represented by the black rectangles shows the improvement in the prediction of the thermodynamic properties of ethane produced by the Bublik equation. The performance of this equation of state was evaluated for several nonpolar substances as well and is very satisfactory for the subcritical region and satisfactory for the supercritical region. Now we present the three equations of state that belong to the third group of improved equations of the von der Waals gases and fluids, where both the repulsion term and the attraction term are modified. The first one is derived from perturbed hard chain theory with the acronym SPHCT, which is a synthesis of polymer solution theories and perturbed hard sphere theories. Polymer solution theories lie on the assumption that we can consider a real polymer chain as composed of two components, an ideal chain providing the entropic contribution to the system and a dilute gas of monomers providing the energetic contribution to the system. The core idea of perturbed hard sphere theories is to treat the attractive forces between molecules as a perturbation to the hard sphere potential, which simplifies calculations while still capturing essential fluid behavior. In the simplified perturbed hard chain theory, a simple analytical equation for chain-like molecules interacting with square well potential is derived by replacing the complicated attractive term in the perturbed hard chain theory. One of the several equations of state based on simplified perturbed hard chain theory was proposed by Περὶ and Prausnitz in 1975 to describe critical equilibria, and we show it in the form introduced by von Pelt, Peters and Ahrens in 1992. For a one-component system, the repulsion term of the SPHCT equation is given by the gas constant R times the temperature T over the molar volume Vm times a volume correction factor equal to 1 plus a constant C times 4 times eta minus 2 times eta squared over the cube of 1 minus eta. In fact, this factor is the generalized version of the Carnahan-Starling model for hard spheres, where eta denotes pi times square root 2 over 6 times V star over Vm. And V star is the close-packed volume per segment in the chain and given by the Avogadro's number Na times the number of segments per molecule S times the cube of the hard sphere diameter d over the square root of 2. The parameter C is equal to 1/3 times the degrees of freedom of one molecule. For spherical molecules there are only 3 translational degrees of freedom and C is equal to 1. For molecules permitting internal vibrations and rotations the value of C is greater than 1, like in the case of N-decane where C is equal to 4.1717. The attraction term in the SPHCT equation of state is equal to minus the R times T over Vm, times Vm times C times V star times Y over the sum of Vm and V star times Y. Here Zm denotes the close packet coordination number of the molecule counting the number of its neighbors in a close packet structure of the molecules of the medium. The quantity Y is defined as the exponential function of the intermolecular potential energy per unit area epsilon times the surface area of the molecule Q over C times the Boltzmann constant K times the temperature T, minus 1. By applying this equation of state, good results can be achieved particularly for vapor pressures and saturated liquid densities of N-alkanes, but its accuracy can decrease near the triple and critical points. In the figure we can see the calculated vapor pressure versus temperature curves of normal alkanes with the carbon number N over the regime where this equation gives reasonable description for alkanes, as shown by the black squares representing experimental data. The next equation of state introduced by Christoforakos and Franck in 1986, and Heilig and Franck brought it into a more general form 3 years later by incorporating several types of the repulsion term based on the Carnahan-Starling hard sphere model into the equation of state. The repulsion term in the equation of state has a generalized volume correction factor given by the ratio of the cubic polynomial of the molar volume Vm with the coefficients F1, F2 and F3 to the cube of the difference between Vm and F0. The attraction term has the pressure correction factor G0, which has different forms for the original and the generalized versions of the equation of state. In the original equation of state, this factor describes the effects of a square well potential model of attractive forces between molecules, and it is defined by 4 times beta over Vm, times lambda squares minus 1, times the exponential of the energy epsilon over the Boltzmann constant K times the temperature T minus 1. Here lambda is the relative width of the potential well whereas epsilon characterizes its depths, and beta is a function of the temperature given by a factor depending on the critical temperature Tc of the substance times a ratio of Tc to the temperature T to the power 3 over 10. In the generalized version of the equation of state, G0 is equal to the ratio of capital B to the sum of Vm and capital C over capital B, where capital B and capital C are the second and third virial coefficients of a square well fluid molecules, respectively. In this table we present the explicit forms of the coefficients F0, F1, F2 and F3 of the polynomials of the molar volume in the repulsion term for different equations of states using hard body models of the repulsive intermolecular forces in gases and fluids. The first line in the table shows the coefficients for the Carnahan-Starling 1 fluid model combined with quadratic 1 fluid mixing rules, which are relations used to average the parameters of an equations of taking into account the mixture composition as seen in the definition of the molecular volume parameters beta, beta x, and beta sub ij. Here xi denotes the mole fraction of the component I in the mixture and d sub ij is the average of the molecular diameters of the components I and j. This equation of state has the simplest polynomial expression in the numerator of the volume correction factor as the coefficients are simply beta x raised to different powers. The second model in the table is called Mansouri-Carnahan-Starling Lefand equation of state, in which the effects of increasing differences in sphere size at high densities are taken into account. Here the coefficients contain beta raised to different powers and the molecular volume parameters y1, y2, and y3 describing the mixing rules of the different diameters di and dj of the components I and j. These parameters evidently also depend on the mole fractions xi and the parameter beta sub ij. The third line of the table displays the coefficients for the Bublik hard convex bodies equation of state, which also allows the deviation of the molecular geometry from sphericity, as already seen. The coefficients contain the spherocylinder parameters alpha1 and alpha2 characterizing these deviations in the mixture depending on the molar fraction xi, the diameter di, and the volume parameter beta sub ij. The last model shown in the table is the perturbed hard chain theory equation of state, where density-dependent degrees of freedom for rotation and slow vibration are also considered in addition to the anisotropy of shape. As a result, besides the molecular volume parameter beta x, the polynomial coefficients contain the parameters f1 and f2 describing the non-translational density-dependent degrees of the molecules in the mixture. In fact, there is an additional equation of state derived from the chain of rotators theory, another possibility from which the difference between equations of state for hard spheres and hard convex bodies can be derived. The repulsion term in its equation of state can be written as the linear combination of the repulsion terms of the Carnahan-Starling 1 fluid model and the Bublik hard convex bodies model, where the coefficients are 1 minus 1 over 2 times f1 and 1 over 2 times f2. The last equation of state presented here is the Dieter's equation of state, which is a semi-empirical expression with several parameters from 1982. In the repulsion term of the equation, Dieter's modified the Carnahan-Starling approximation for rigid spheres with the parameter eta such that the compressibility factor derived for that part could have better fit to experimental data by introducing the parameter C0, besides the correction C for non-spherical shape associated with the non-translational degrees of freedom of the molecules. C0 is a constant value obtained from fitting the equation to the argon data, which accounts of soft interactions. The attraction term of the Dieter's equation of state also uses the square well intermolecular potential, where a semi-empirical approach is chosen to separate the effects of hard spheres or square well particles at infinite temperature from the effect of point molecules with attractive potential at finite temperature and low density. The later describing the effect of the attractive potential of the point molecules gives the exponential part of the attraction term depending on the reduced temperature T bar given by the parameter C times the temperature T over the pressure correction constant A, which is also equal to C times the Boltzmann constant K times T over the well depth epsilon. The part describing the effect of spheres in the attraction term is expanded in polynomial series since the original equation of state could not be integrated analytically. As a result, the constant H0, the factor gamma denoting 1 minus a constant time the square of C minus 1, and the third term denoted by F sub I plus 1 appear in the equation of state. The third term depending on C and T bar contains the sum of expansion. In order to evaluate the equation of state, the mixing rules for the parameters A, B, and C describing the dependence of the parameters on the composition of the substance have to be known. Dieter's also plotted the pressure versus temperature diagram of the systems propane carbon tetrafluoride and butane carbon tetrafluoride to compare the calculated curves for the critical lines with the experimental data represented by the black rectangles. The Dieter's equation of state can be used to accurately predict the vapor-liquid properties of binary mixtures. However, at the vapor-liquid critical points, reliable results can only be obtained for mixtures of molecules of similar size from this semi-empiric model. In the end of this presentation on real gases, we give a summary of the topics discussed here. We started with the introduction of the compressibility factor of real gases defined by the ratio of the molar volume of a real gas at given temperature and pressure to the molar volume of an ideal gas at given temperature and pressure. By definition, the compressibility factor is equal to 1 for ideal gases, and its deviation from 1 describes the deviation of the behavior of a real gas from the ideal gas law. We saw that the compressibility factor depends on both the temperature and the pressure of the medium. A real gas is highly compressible at low pressures with a volume lesser than the volume of its ideal counterpart, whereas at high pressure real gases become incompressible. We also presented the Burnett method, which is an iterative measurement process of gas pressure and volume to determine the compressibility factor of a real gas as a function of its pressure at a given temperature. Then we discussed the effects of the von der Waals forces, that is the weak electrostatic forces between the molecules in a gas which are approximated by two opposing forces, a long-range attraction and a short-range repulsion in molecular interactions. We presented the von der Waals equation of state for real gases with a repulsion term applying volume correction and an attraction term applying pressure correction on the ideal gas law based on this approximation. The thermodynamic state of von der Waals gases is described by this cubic equation depending on the two von der Waals constants specific for a given substance related to the two types of corrections compared with the state of an ideal gas. We saw that for the cubic equation of state a critical isotherm with one point of inflection separates the monotonic decreasing isotherms from those having a local minimum and a local maximum in the pressure-volume diagram. The temperature of the critical isotherm is the critical temperature of a given von der Waals gas and the point of the inflection on the critical isotherm is the critical point of the gas. We determine the state variables of the gas at the critical point called critical constants such as the critical temperature, pressure and volume of the substance. We also express the von der Waals constants of the gas in terms of its critical constants, and presented the measurement method of the later constants by applying a critical point apparatus which allows us to determine the von der Waals constants of a given substance as well. Besides the compressibility factor at the critical point, the critical constants were presented in a table for several substances from the simplest monoatomic gas like helium to the ones composed of more complex molecules like alkanes. We discussed the dependence of these critical variables on the complexity of the molecules and discussed the deviation of the critical compressibility factor from the universal value predicted by the von der Waals approximation. We established that below the critical temperature there is an unstable region of negative compressibility for the isotherms with a local extrema in the pressure-volume diagram, where an isotherm cannot describe an equilibrium state for the substance. In this unstable region the phase transition of the substance can take place at constant pressure and the gas and liquid phases coexist. That is, a gas compressed at constant temperature through these volumes will condense with the volume decreasing at constant pressure. In order to describe this phase transition in the unstable region, we presented a graphical method called Maxwell construction correcting the deficiency of the von der Waals equation. As we saw, this method determines the phase boundary in the pressure versus volume diagram for the equation of state by applying the equal area law, which replaces isotherms in the unstable region with isobaric horizontal lines connecting the saturated states of the medium such that the areas cut above and below this line are equal in the diagram. We also talked about the Gibbs criterion for the change in the free enthalpy or the chemical potential of any substance during its phase transition, providing another method to address the issue with the von der Waals equation in the unstable region, which is equivalent to the Maxwell construction. As a result, both of the approaches replace the von der Waals isotherms with the broken curves of physical isotherms. Then we define the reduced state variables of a gas by the ratio of its state variables to the corresponding critical constants of the gas, and derive the reduced equation of state in terms of the reduced variables from the von der Waals equation, which is an equation free from the von der Waals constants that is universal for all substances. Based on this finding, we could establish the law of corresponding states telling us that there exists a universal equation of state containing no arbitrary constants if expressed in the reduced variables describing the thermodynamic state of the substance. In other words, substances behave alike at the same reduced states. We also presented generalized charts for the compressibility factors using reduced variables compiled from experimental data for different substances. Then we determined the internal energy of real gases by using the von der Waals equation of state and applied the result in the first law of thermodynamics, pointing out that in the Gay-Lussac Joule experiment on the free expansion of air the gas must cool down. Motivated by this result, we described the Joule-Thomson effect, which is the change in the temperature of a real gas as it expands through a porous plug in an insulated chamber. Here either the cooling or the warming of the expanding gas can be measured. We showed that such a process is an isenthalpic process, as opposed to the Phi expansion of the air where its internal energy remains constant. We also introduced the Joule-Thomson coefficient as the partial derivative of the temperature of the gas with respect to its pressure at constant enthalpy. By definition, its sign determines whether a real gas cools down or warm up during its expansion. We expressed this coefficient in terms of the von der Waals constants and used it to determine the inversion temperature and the inversion curve separating the two domains of cooling and heating in the pressure versus temperature diagram. We also calculated the entropy of a real gas in von der Waals approximation, and as in the case of the internal energy we obtained a term which is present in the expression derived for an ideal gas, and another term with the contribution from the volume correction. We saw that in the case of free enthalpy we have contributions from both the volume correction and the pressure correction. Then we introduced the fugacity of gas as the effective pressure, which gives the measured value of the free enthalpy of a real gas in comparison with the value obtained for an ideal gas. We define the fugacity coefficient as well by the ratio of the fugacity to the pressure of the gas, and expressed it as the integral of a function of the pressure and compressibility factor of the gas. We provided generalized charts of the fugacity coefficients for many substances as well. Finally, we presented some of the improved equations of state as the modifications of the von der Waals equation, applying a more realistic description of the intermolecular forces in real gases, vapors, and liquids, which are frequently used in thermodynamic calculations. Because these modifications can essentially be two types, improving either the repulsion term or the attraction term, we divided the improved equations of state into three groups: cubic equations of state where the attraction term is modified, non-cubic equations of state where the repulsion term is modified, and non-cubic equations of state where both the terms are modified. We shortly summarized the principles used in these modifications, and provided some comparisons with the predictions of the von der Waals equations and experimental data demonstrating the improvements achieved with them.